So we're on the hour. I think it's time to start. Welcome to WHPI. This is the session 5 of WHPI, and we will be talking about various issues related to the campaigns. And I'm Chair Fran Bagnall of the University of Colorado. We have Noor Raoufi as a co-chair, and we will be starting off with a quick explanation of a reminder of how to use Slido, which is our source of doing questions. So Noor is going to monitor the questions that are going to be, we would like you to encourage you to put all the time in Slido, and then we will move into a discussion of how to access virtual resources that Barbara Thompson will run with Ian Hewins. So let's start off with a quick introduction to Slido. Kelvin, if you could give us a lead through how this works, and then we'll get on with the session. Thank you very much.
Thank you. Let me start by sharing my screen. So in a moment, Catherine and I will be sharing a link that will take you to the participant interface of Slido, which is this what you see here right now. So we would like all of you to use Slido for all of your scientific questions. You'll type your questions in the box here and send it on its way. You'll notice that presenters are able to also reply to your questions by clicking on the reply item. We would also like all of you to click on the little icon on the top right corner, and this will take you to your profile. We would like you to put in your name, email address, and once you save it, the next time you try to type in a question, you can either type it as yourself or you can choose to be anonymous. We prefer that you use your name so that we can refer to you back during the Q&A session, and we're able to call you live to ask a question. And that's pretty much it. So I'll give it back to Barbara Thompson. So take it away, Barbara. And Barbara, I think you're muted.
Yep. Hi, everyone. Yeah, sorry, I got a course and update notice for my computer just like 30 seconds ago. So anyways, so can you see everything?
We can.
Yes, we can.
Great. Okay. So welcome, everyone. Again, I want to remind you throughout this workshop that as you learn about all the exciting things that people are doing, you should be thinking of what we're going to do afterwards, because WHPI is all about sharing and collaborating on data and models to forward heliophysics science and planetary science. And so, as you know, this is the WHPI is an international initiative. Our focus is to understand interconnected systems, which means the challenge of comparing different data sets and models. In the previous two efforts, Whole Sun Month and Whole Heliosphere Interval, we did large type of mosaics like Ian Hewins described yesterday, where we combined many data sets to give context for what things look like. And now this campaign is the project, WHPI and these associated campaigns are supported by the HSO Connect program. And so if you see HSO Connect, that is the NASA program that supports WHPI. And it's the access part, the data and model access part of WHPI. So for one thing, over the past over a year, people have been putting together these show and tells, which are online tutorials on how to access and use individual assets that will be essential for WHPI coordination. And so, however, now that we have, we're starting to build a library of how to use these things and these tutorials, there are different elements to data and model access. First of all, there's the stuff that you are working on. How do you share the data and the models and the things that you're working on? The second thing is, how do you find the tools that allow you to collaborate and connect these things? And finally, how do you find collaborators? How do you find other people that are working on similar things, and how do we coordinate these efforts together? And so it requires a three-pronged approach. The first, so if you want to collaborate with people, you have to look for a way to share and coordinate these things. And before you can even start that, you want to be able to locate what people are doing and understand what's out there. So there's three tiers to this. There's three aspects to it. The first one is the HSO Connect data and modeling portal. That's the thing that you're going to use to access, but I'm going to skip that for now because I'm going to show you a demo in a little bit. The second aspect is if you want to access data, actually, let me do that now. That's a smart thing to do. This is our HSO Connect WHPI data and modeling resource portal. This is it's a live site, and I will be sending around the links and the access soon. You can submit a resource. And what this does is it's an Amazon.com type library of different things that people are contributing to this to the library. And so the way you can do this is you can say, you can type sun in here, and it will pull up the entries that have the word sun. So it works like Amazon, that you can put in a query, you can put in a parameter, and it will limit what it returns based on that parameter. Right now we don't have a huge amount, so I can't do anything. If I put in something, well, I guess I can put magnetic, if you want to see magnetic fields and things like that. There's a couple ones that have magnetic activity or magnetic field. There are flags. If you want, you can limit it to only one area of the only one physical regime. So if you want to see the heliosphere, oh, we don't have any yet, you guys. Come on, you guys got to send me some. Let's go to upper atmosphere. We have, you can limit that, and then it'll only show you. And so it's like a filter, just like Amazon.com. If you've used that, you can set a filter, and it'll filter for these things. You can also look for contributions to particular campaigns. If you did the if you're interested in the 7th perihelion for Parker Probe, that's here. All the campaigns are described on the WHPI site and will be in the About section as well, so you'll be able to know exactly which campaign we're talking about. Finally, there's the type of product. There are observation data products. There are services, which are comprehensive services that don't just serve one type of product. They serve a variety of things. There are model or simulation products. There are model or simulation services. Oops, none there yet. And then there are also tools and coding resources, things that don't necessarily serve data, but are things that allow you this connection. In each of these elements, there's different features that you can have. For example, the Dunn Solar Telescope, which Damien has, is it's a data product that has been compiled for a variety of the campaigns. They did do one of the WHPI show and tells, and so I can click on the link, and you can get a nice tutorial from Damien telling you how to use the resource. We have the ability to, if you have a Jupyter notebook, they don't, I just flagged it here so that it would be a good app example. If you want to download the data directly, this is tells you how you can learn about the resource. Basically, it's just the main website that describes it. And discuss is usually a Slack channel or a GitHub Slack type channel. There's also a source code ability. So if you have a GitHub repository, you can link to that too. And so this is and so right now we don't have a huge number of things in here, but as you can imagine, as we start to get hundreds, it's going to be pretty easy and handy to be able to locate these people and what these activities, and see what they're doing. Now, that is how you locate things, but you still want to share data, and you want to share also share code. So we have two aspects to that. To share data, our preference is you work with existing data systems. So if you, and we'll send the link around, if you submit a resource to this and you do not have a repository that you're working with to share the data, we will try to associate you with the nearest data service or model service that can help to serve it if you don't have one that you're satisfied with. However, for specific products, things that we're combining on WHPI, especially the type that Ian was describing yesterday, we do have a cloud, an Amazon cloud service that's coming online. The great thing about this thing is that it's got Jupyter in the background. IDL is going to be installed, and also it will support a binder hub, which means you can execute Jupyter notebooks and things without having to have a cloud account. And so it's a service where we post data, and we can post products and things like that, and we can also post code that you can run on the cloud and use without people having to have a resource. And the great thing is it's Amazon, and so it's sponsored by NASA, but it is not a government site, which means that all the restrictions that people have to worry about are not as severe as you're probably familiar with trying to get an account on a government site. So this is something that has been it's there. There's just a couple of things on it now, but over time, as we start to create sets of data where we're wanting to coordinate together and have it in a similar place, we can use this. So we will. My intern has been creating tutorials. They're here. My intern's been creating these different tutorials to show how. Oh wait. Different tutorials as to how to access and use things on the cloud. Finally, once we've gotten the way to share the data and the things that we're doing, we have there's also a lot of you will want to share code in a way that you can easily integrate other people's code with each other. For most of you, you know that means GitHub. So if you haven't used GitHub, we have tutorials for that too. GitHub works. It's code agnostic. A lot of people think of GitHub as a Python repository. No, there are extensive libraries in IDL, in MATLAB, different any type of programming language you use. GitHub is a way that you can have a repository where you can have code. It is tracked. You can see the versions, and you can update code, and people who are using your code can receive those updates in a consistent manner. There is a hsoconnect.github.io site. We can host code on this. Our preference is not to, because what you want to do is you'd want to create your own site and have your own code be developed by you and updated by you and completely controlled by you, and you just want us on our GitHub site to refer to it. I think and so the HSO Connect GitHub site has we're starting to post some tutorials and some overall overarching code, but my recommendation is to use the tutorials if you don't already have one, to establish your own GitHub site if you'd like to share code. Otherwise, if you want, you can just create a public directory and post the code in there and have a README file. That's fine too. It's whatever you're comfortable with. It's over time. And so let's see. So let's go back. Let's see. And so, yeah, and then so over time, we'll start to post more and more resources into the HSO Connect portal. You'll all receive these links in an email after this meeting. And so don't worry about finding the don't worry about these links. You'll find them. Let's see. And I should say hsoconnect.github.io. It's been updated. It is live. And so I'll send the corrected link for that. But in summary, there's really three aspects to a successful data collaboration environment. You have your data and what you're doing in your code. And so you want to locate compatible people or compatible projects that to collaborate and combine and perform analysis with. That is what the data and modeling portal is for. It's a portal. It doesn't serve anything. All it does is help you find things. So it's a locator service. And again, over time, as we have a lot of these things, it'll be the different aspects to it will help people identify more clearly what's there, and how to, and what's available and who to contact. You want to, once you have this, you also want to share what you have so that people can coordinate and do this analysis together. So again, we have GitHub tutorials, or you can just share directly, whichever way you like. And finally, the WHPI Jupyter Hub is the Amazon Cloud and the Jupyter Hub are online, and they're being and as a result of this meeting, and also certainly afterwards, more and more aspects, more and more things are going to be added so that people can access the cloud, run the code, and get to the data all over the place. So
excellent, Barbara. Very useful.
Yep. All right.
Good.
Thank you, guys.
Great. That's a lot of stuff, but I think once you get used to it, you'll get in there and get your hands dirty and have fun.
I will be having online office hours at different times, so people can just join me when they need to. I'm not going to just, Ian and I are not going to just abandon you.
Excellent. So I urge everybody to put questions and comments on Slido about this. And we're going to move on to the next presentation, which is by Juliana de Toma, and she's going to talk about the overview of campaigns. So take it away, Juliana.
Okay, thank you. So this is a brief overview of the WHPI observing campaign. They are an important component of our solar minimum initiative. WHPI encompasses the entire solar minimum, but these are time periods that are of general interest when we had focused coordinated observation. And they provide an opportunity to work together on common intervals, for example, for model data comparison. So we had 5 campaigns during WHPI. The first one was a campaign in the spring of 2019 on corona holes and the associated high-speed solar wind streams. The second campaign was in conjunction with the total solar eclipse in July 2019. And then we had 3 campaigns during Parker Solar Probe perihelions. So our first campaign was able to capture the end of 2 very long-lived corona holes that were present simultaneously on the sun for many solar rotations from 2018 to 2019. And this time corresponds to the declining phase of the solar cycle, the beginning of the solar minimum, when large corona hole at low latitude are commonly seen on the sun. And they're sources of solar wind at the Earth. So the 2 holes were one predominantly in the southern hemisphere was a very large hole that extended into the northern hemisphere. The other one was started as an extension of the north polar corona hole, then it detached and joined with another corona hole, becoming a large transequatorial hole. And we have seen some of the talk yesterday that there were clear periodicity associated with this corona hole in the solar wind. The high-speed stream were also sources of minor geomagnetic storm on Earth and enhancement in the radiation belt. The second campaign was centered around the total solar eclipse. This was an obvious time to choose. We had an eclipse during minimum. Eclipses are a rare opportunity to observe the low corona, so we have virtually all solar observatories that look at the sun during this time. And we had eclipse expedition. LASCO was running a special program. And we also had a number of facilities, geospace facilities that joined the solar observatories. The eclipse was in the South Pacific and southern South America. And this is, for example, a map of the response of the thermosphere from the GOLD satellite. And together with this observation, there was a very significant effort in terms of modeling, both in terms of solar model and model of the upper atmosphere to understand the response of the Earth atmosphere to the eclipse.
Hey, Juliana, are you, we're not seeing your slides advance. I'm just checking. I think you actually did have slides that advanced after this first page.
Oops, they're not advancing.
No, you're on the first page.
Oh, I have the same problem. The
Yes, the
resolution.
problem Ian had. So sorry, you might need to go out and come back in.
Oh, sorry. I am very sorry. Let me try to share it again.
Yeah, that worked for me.
Okay, so you see the first one now.
You need to share again.
Oops, I think I am sharing. Sorry.
There you go.
Yeah, we see it.
Okay. So this is my second slide on the corona. No, actually my
Yeah.
third.
We
Okay.
we don't see it. Would you like me to share for you?
Yeah, because I don't know. I don't know what
Okay.
to do then.
Let me try sharing for you.
Let me stop sharing then.
All right.
Okay, Karen, can you go to the second page?
Yes, for some reason I'm having a similar issue. Let me stop sharing here. Let me share again. Apologies. Okay,
Standard IT solution. Turn it off, turn it back on again.
there we go. Can you see the slides advancing?
Yes,
Should be
I
able to
saw
see it.
the,
Okay,
yes.
great. Okay, Julie, let me know which slide you want me to.
Yeah, if you can start. Oh gosh, I'm sorry to spending all this time.
No problem.
So this is the slide about the eclipse. I was showing a map showing the effect of the eclipse on the thermosphere. And then if you go to the next slide, I was mentioning that there was a significant modeling effort in conjunction with the observation both from the solar side and from the upper atmosphere. And then if you go to the next slide, we had three Parker Solar Probe campaigns. The fourth and the seventh were during the perihelion campaign, were during a time when Parker was nearly radially aligned with the Earth. And so this was a unique opportunity for coordinated observation. This was our largest campaign, and Noor will talk more about that. And the third Parker Solar Probe campaign was during the 8th perihelion and focused on high resolution observation of corona holes. And we had many large solar telescopes, including Gregor, the Swedish Solar Telescope, Big Bear, and the Dan Solar Telescope, they join, and many radio observatory and other observatory as well. And then if you go to the next slide, and Stefan will talk more about this campaign. So I just wanted to say that WHPI role was to support the Parker Solar Probe team. We help with the organization of activities ahead of the campaign, including coordinating the ground-based observation. During the campaign, we posted on the WHPI website target information for the solar telescope to know where to point. And we had about 40 ground-based observatory around the world, many satellites, and about 600 participants. We also had a fantastic modeling team that worked really hard to provide prediction every day that we could post on the web. And I wanted to thank you, all the people that joined the campaign, all the observers, all the modelers, and this was only possible because of your participation. And then if you go to the next slide, this is my last slide. I don't have time to read aloud all the names of the contributors, but I'd like just to acknowledge them. And the next step now is to work on the science of all this. We have a lot of observation that we acquired, and so we hope this workshop will be an opportunity for us to start collaboration and work together. And this is all I have, and I'm passing it to Noor now.
So next we have some comments from Noor and from Stefan.
Okay, do you see my slides?
We do.
Okay, excellent. I'm waiting for it to come on my screen. Okay, excellent.
You'll need to switch displays. We see your presenter mode.
I'm going to do that. Is it better now?
Perfect. Yes, we see it perfectly.
Okay. So good morning, everybody. And as Juliana was mentioning, the campaigns for Encounter 4 and 7 and 8, they went really, we cannot have hoped for any better. We got a lot of support from all over the world, and why we are going for some reason it's not. There was a movie here. The movies are not playing for. Anyway, the movies are disappearing for some reason. Why Encounter 4 and 7? And there is actually other encounters that are coming. I will talk about the next one at the end. These we can see the whole encounter as Parker Solar Probe is crossing the solar disk from east to west. And there are a lot of good opportunities for. I don't know what is going on. The movies disappeared for some reason. Anyway, we see the Parker Solar Probe crossing the whole solar disk from east to west, and there is a lot of opportunities for synergies with ground-based observatories, but also with space missions out there. And to our great surprise, when we solicited support for Encounter 4, we honestly were hopeful just for a handful of observatories here and there to support us. But to our great surprise, we got tens of observatories around the world and also space missions supporting us. I think for Encounter 4, we got over 40 observatories in total. And for Encounter 7, we got over 50 observatories. And here I'm going just to flip through the slides, just as Juliana mentioned earlier, just to acknowledge and thank all of you out there who supported us, that this was a great effort from everybody. And I'm pretty sure that the data we got from there will be useful for many years to come. So these are all the people in the observatories who participated in these campaigns, and I hope I'm not missing some of you out there. As I said, for Parker Solar Probe on our side, we are collecting a ton of data throughout the orbit. And we are looking for collaborations with all of you out there, who, whether you participated in these campaigns or not. We are open to collaborations. And please, if you need our help, do not hesitate to get in touch with us. We are so eager to help anybody to do science with our data, but also with the data we collected during these campaigns from ground-based observatories in space missions. Let me now go very briefly to talk about Encounter 11. Why Encounter 11 is similar, but in a way it's better than Encounter 7, and it's not better, but it has some more benefits to science, probably more than 4 and 7. There are two reasons. In terms of geometry, for Earth, it's similar to Encounter 4 and 7. The additional thing this time around, we have Solar Orbiter. Solar Orbiter, as you can see it here, it's there. It will be supporting us for the whole period. We will be working together. In the future, we'll have Pipi Colombo, but Pipi Colombo is still in cruise phase, so we'll get probably some magnetic field data from them. But as I said, from Earth, Solar Stereo, Solar Orbiter, we have plenty of synergies to do there. And actually, we have a special program with Solar Orbiter that will be running during this encounter. Two other things that are new for going forward. Parker Solar Probe now is flying through the sub-Alvinic solar wind, and we have not done this before for the first 7 encounters. But starting from Encounter 8 and 9, we started seeing the sub-Alvinic solar wind, and that is brand new science that we have not seen before. I mean, probably we are seeing it for the first time. The other thing also is that solar activity is picking up. For Encounter 4 and 7, the sun was pretty quiet, but hopefully now we will get some events during those encounters that will be extremely nice. And there, when we are doing science with the probe orbiter, and we will need a lot of context and supporting data from all sorts of data to make sense of what we are seeing. Just to conclude, this is another forum that we have for collaborations, and this basically target early career scientists. We call it the Parker Solar Probe Scholars, but it's not limited to Parker Solar Probe science. It's open to all heliophysics, and the main goal here is to promote early career scientists. We had 2 meetings so far, and the 3rd meeting is coming in November. It is basically a platform where early career scientists come and share their research with everybody around there. We have over 350 scientists from all over the world, as you can see it here, join the program. And please, if you have science and all heliophysics you want to share, please get in on this. The last slide I have is about Parker 2 conference, which will be June 21st, 24. And there again, I would love to have at least 1 session or even 2 about these campaigns that we are doing here. And I encourage all of you out there, if you have science about these campaigns, please submit abstracts to the conference, and we will have, as I said, at least 1 or 2 sessions about these campagns. Thank you very much. And
thank you. Let's move on to Stefan. We are a little 1 minute over. I'm going to give you 3 minutes to get through your slides, please. Stefan, we're seeing your slide.
Stefan, I think you're muted.
Yes, I'm unmuted, so perfect. So hello everyone. Basically, we just performed a small campaign for solar observations during PSP's 8th perihelion. The idea was to connect coronal holes to what Parker Solar Probe sees. And for only being a solar observing campaign, we became pretty big. We started with something like 10 people. In the meantime, we are more than 40 people. We had basically all of the 4 large solar telescopes at that time, so excluded of DKIST at the point, some radio observatories, and so on. The big problem we want to basically tackle is when you are thinking about forecasting high-speed streams, the effects, stream interaction regions, angelic particles, the basic idea of that is known. The big issue with the propagation of high-speed streams is close here to the sun. It's something like 0.1 AU. We need to be able to understand and predict the properties of a high-speed stream at this distance if you want to model its propagation in interplanetary space and all of its effects. And there we are really having large problems. So basically what we wanted to do is, sorry, I'm a little bit jumping here at the moment. We want to look on the right image. We want to make as many slices through a complete coronal hole as possible. So really looking from the photosphere, several slices to the chromosphere, transition region, corona, look at fit effects, look at abundances, at plasma outflows, basically at all of the stuff which we can get on coronal holes to relate all of these things. Here on the left slide, you can see the target coronal hole which we wanted to observe. This was on April the 30th, and Parker Solar Probe has been only a little bit behind. So Parker Solar Probe should have been able to see this high-speed stream. I already got a peek on the PSP data. I'm not sure if you've seen it or not. We see some features. Maybe we've seen even something which could come from it, but we definitely need further analysis. So basically, we got the 4 large solar telescopes. Each of the telescopes has only a small field of view, something like this you see here on the right side. So basically what we had to do is a large mosaic, taking something like observations of something like 50 to 60 different positions to raster the complete coronal hole. We have all of this complete coronal hole, iris observations, node observations, radio observations, and of course PSP. PSP was outbound, so we are not anymore at 15 solar radii at that point, but we are still pretty close. What else happened during PSP's 8th perihelion? And since we grew much larger than we thought in the beginning, I think we will also have a look at most of that. There have been some features seen by PSP, and you already said that. I think the most interesting point is we have crossed our Fennec point. PSP really dipped into the magnetic corona, and this opens completely new opportunities for solar physicists. Second thing what happened is the complete magnetic reconfiguration of the corona. So you can see this corona hole here on 30s, and a few days later, and it started to strongly rotate differentially. We have several small type 3 radio bursts, and on May the 8th, there has been also BNC8 flare with a type 3 radio burst, which was observed. And so I can only say everyone who wants to join is welcome. Write me an email. I think in something like 1 month, we will have a small workshop where we will go more into details and discuss the science. Everyone who still wants to join is welcome.
Thank you very much, Stefan. This is fantastic. This is great science. So we need to move on to the next talk. We're now going to move into scene setting, working group 3, starting off with comparative solar minima. We're running 5 minutes late, so I want to get started. David Hathaway is going to start, and then Janet Kazira will do the second part. So David, are you ready to take it away?
I am.
Excellent. We see your slide. Put it into, there we go.
There we go.
Excellent.
All right. Doesn't work so well on my screen, but hopefully it works on yours. Really appreciate this opportunity and thank the organizers for inviting me. Most of you will be familiar with some of the things I present today, and some of you will be familiar with most of it. But bear with me, because when I get to the end, I'm going to have a challenge for this community. This is a short history of the sun's magnetic field that we've had for the last 4 cycles. We've had these daily measurements since the mid-70s from multiple observatories. We've had a few occasional observations going back to the mid-50s or early 50s from Horace and Harold Babcock's. This tells us a lot about the sun. It's the boundary condition for the heliospheric fields and winds, but we'd like to have much longer records, of course. Sunspot activity, radioisotopes and tree rings and others help to fill in the longer record. This is kind of a mission statement for me. My own interest is in the solar dynamo, and conditions at minimum reveal a key dynamo characteristics, mainly that field conditions at minima are predictors of the size of the following cycle. So what I'm going to do is, first of all, start off with the sunspot cycle, show you how the cycles overlap to varying degree at minima, and given that overlap, there are relationships between the cycle minima and following maxima. I'll then talk about a slightly shorter data set, the geomagnetic activity, and look at it at minima vis-a-vis the following maxima, and then finally get down to the last 4 cycles in polar fields at minima. So here's the sunspot record. These are yearly sunspot numbers on the top, going back 400 years, showing the 11-year sunspot cycle and the 100-year Gleisberg cycle in both rise and fall of maxima and rise and fall of minima. The bottom panel shows the 150 or so year record of sunspot areas and positions that provide more information, in particular show the overlap between cycles, that we can go in and I can separate them with these lines in these diagonal lines. All of these diagonal lines have the same slope. It's just a different intercept from cycle to cycle, but does a pretty good job of separating active regions of one cycle from the next, so that we can look explicitly at the overlap. So here is sunspot area as a function of time. I've separated the cycles as I've shown in the last slide. The odd cycles are in blue and plotted positively. The even cycles are in red and plotted negatively. Each is offset by about 0.01%, so that they don't lie on top of each other at minima. But you can see from this the overlap at minima from cycle to cycle. It's typically something on the order of 1.5 years or so. One key outlier is cycle 19 over here, which had a very short overlap with cycle 18. Cycle 18 basically just died and cycle 19 came on real strong. So there's very little overlap there, and that influences some of the statistics we have for that minimum. Given the sunspot numbers, you can look at things like the size of the minimum, how low did the minimum go in smooth sunspot number, and plot that. Here is a function of the sunspot cycle maximum, and there is a trend that the minima are small prior to small cycles and large prior to large cycles. There's a lot of scatter, as you can see in this. Cycle 19 is again an outlier. It had a much lower minima than you might have been expected given its size. Just to note, there is where cycle 25, the minimum 2425 came in. So that's suggesting a fairly small cycle 25, but again, huge scatter. At that level, it can be anywhere from 70 to 200. So not a good predictor. We can also look at cycle length. There's an inverse relationship with small cycles being preceded by a long cycle, and big cycles being preceded by short cycles. Here again, there's a fair amount of scatter. If we put in cycle 25, it's right there in the middle. Again, it's not a good predictor. It says that cycle 25 ought to be average, but it can be anywhere from 125 or so up to 250 for a peak sunspot number. So again, not a good predictor, but these two aspects reveal a key characteristic that we can take away from the sunspot number, and that is that large cycles tend to start early and leave behind high minima, and this is largely as a result of the cycle overlap. Getting on geomagnetic activity, geomagnetic observatories have been obtaining observations since the early 1800s. There was a global network of 2 stations, one in England and one in Australia, that has operated with some slight changes since 1868 and provides data on over the course of 3 hours how much the geomagnetic field changes at those stations, and produce what's called the AA index. Again, they moved stations a couple of times, so there are some adjustments that need to be made to make it uniform. But this is the data set in blue on the top, the AA index, and the sunspot number on the bottom. Ohl in 1966 noted that the minima in the AA index that occurs at about the time of sunspot cycle minima tends to be a good predictor for the size of the next cycle. In fact, it's a very good predictor. So here is that value, the AA index at minimum, versus here the maximum in the sunspot area. There's a pretty good linear relationship between it. Here again, cycle 19 is kind of out of line in that it's lower than you might have thought given the size of cycle 19. But again, a fairly good relationship between the geomagnetic activity at minimum and the size of the next cycle. There is where the AA index minimum was. It's the minimum for cycle 24, 25. And again, this is indicating a small cycle, maybe somewhat larger than cycle 24. All right, so if we look at magnetic fields, again, far more information, but a smaller number of cycles. So here I've taken measurements from the Kit Peak 512 channel magnetograph. Later on their SOLAS instrument, and then both MDI and HMI to fill this in. And you can see in particular with cycle 24, It's much better resolution than early on, but it shows it shows a wealth of information about the solar dynamo. They say a picture's worth 1,000 words. This picture's worth at least a dozen papers. There's a lot of information in this, but the main thing we'll concentrate on today are the polar fields, which of course reverse at a time of maximum and build up towards minimum. However, in spite of all of the wealth of detail there, Wilcox Solar Observatory is the preferred data set because it is a single instrument. They have gone to great lengths to account for scattered light and other instrumental effects. So this is a data set where, in this case, we're showing the dipole strength. So you multiply by the sine of latitude and integrate over your data to get the dipole moment. It's or cosine latitude. Sorry, no, sine latitude. So that it's highly weighted towards the polar fields. The blue lines on here are picking out what the axial dipole moment is at the time of minima. You could see if you slid that line forwards or back in time a little bit, you get a slightly different answer, but it does characterize the dipole moment at the time of minimum. And you can see from this the change in strength from cycle to cycle. So this is probably the simplest plot I've ever made with only 3 points on it. Unfortunately, that's all we have. They do fit in pretty nicely along a straight line. I apologize for not putting error bars on there, which just realized yesterday that I hadn't done that. But it's a good straight line between these things that indicate that the dipole at minimum is a good predictor of the size of the next cycle. If we put cycle 25 on there, it now appears that it ought to be, again, similar to cycle 24, maybe a little larger. We can also look at the polar fields here again from Wilcox Solar Observatory, where in black is the polar fields. This is in their northernmost pixel, 55 degrees and higher. The solid line is for the north, the dashed line for the south, and then the blue lines show the range at minima, the size of the polar field in the north and in the south. So we can take that data and produce another very, very simple plot, again, showing 3 points, but 3 points falling fairly well along the line. I mean, this is almost as good as Orion's belt as far as 3 stars right in a row. So again, this is even though it's a small number of samples, it's a pretty good indicator that the polar fields at minima are predictors for the size of the next maxima. There's where cycle 25 is as far as polar fields. Again, basically the same answer you get with the axial dipole, that suggests that it'll be about the size of 24, maybe somewhat larger. Lisa Upton and I, back in 2016, wrote a paper where we tried to predict the polar fields at minimum before minimum. We used our advective flux transport model with flows that were well constrained by observations to simulate the evolution of the sun's fields and look at the polar fields, and in this case, the axial dipole from early 2016 to the end of 2019. We had to put in new active regions, and we chose those from cycle 14, which is a similar size cycle. And we did 32 different realizations with different active region tilts, different convective patterns, and 2 different meridional flow profile changes over the remainder of the cycle. So the bottom left is the figure from that paper with the blue and green lines at the end showing our prediction for what the axial dipole should do. And then on the right is the observation. So we did pretty good, indicated that cycle 25 ought to be similar to cycle 24. This work suggested that maybe slightly smaller.
David,
All
I'm
right.
sorry to interrupt. If you could wrap it up, we've got just about a minute left.
That's why I'm doing conclusions.
Thank you.
Yeah. So to conclude, small cycles tend to start late and leave behind a long cycle and a low minimum sunspot number. Geomagnetic activity at minima are also good predictors of the strength of the following cycle. And here's where I have the challenge that these minima seem to be proxies for the polar fields and the axial dipole. And so my question and challenge is, can this be shown via modeling of recent well-observed minima? I did notice a poster by Irina Belenko, observationally showing that this was the case. It would be nice to nail this down because there's much more geomagnetic data. Then the polar fields and axial dipole at minima appear to be good predictors of the cycle. This is only based on 3 cycles, but it's supported by dynamo theory that the fields at minima are the seeds for the next cycle. And then final conclusion, cycle 25 will be another small cycle like cycle 24. So with that, thank you very much.
Excellent. This is excellent overview. Please put your questions in Slido. We're going to move on to the next speaker, which is Janet Kazira. And I believe that
Janet, you'll have to mute your phone or another device that you have on. Let's see. Janet, can you hear us? Janet, you can unmute your computer.
I was trying to come in through the phone because sometimes I lose my audio.
Okay.
Can you hear me now?
Yes, we can hear you perfectly, and I have your slides up.
Okay, great.
take it away.
All right, so I'm going to try to do the geospace part of this, so just let me get moving. Next slide. I have sat there and thought about what are the most important things to consider when you're trying to understand how geospace is being affected by high-speed streams and how those high-speed streams are changing with the solar cycle and with the variable cycle. So what you really want to do is you want to understand how much energy is entering geospace, and also how you check the coronal holes to Earth, how the high-speed streams are developing, and what are the linkages in geospace. Next slide. So here I just want to show that the amount of energy that's entering geospace has really decreased from solar cycle 23 to 24. And even from 22. And so we're dealing with a lot less energy input, which has implications for the way geospace is going to reconfigure itself with that much energy available. And so if you look up, you can see that there's a list of how much reduction there has been. That's reduction with respect to solar cycle 23. So the sunspot number went down 36%. The magnetic energy density in the solar wind, 63%. The coupling function, 54%. Some of the current systems went down 30 to 40%. The Mach number is, the lowest Mach number is 6.8. The Mach number is greater than 6.9. The alphane speed went down. The distance to the magnetopause, Chapman-Ferrara magnetopause, is 10.6 RE. And you can see in the bottom plot there, this is the energy integrated over each of the solar cycles. And you can see that it's dropping significantly as we move through these last 3 solar cycles. Next slide. And what I wanted to show here is that has implications. These are the normalized distribution functions, probability distribution functions. They're normalized by how many hours of observations in each cycle. There's DST on the left side, and there's AE on the right side. and it's in percent. So if you added everything up, each panel would be 100%. It tells you how many hours there have been, that particular amount of activity has existed in that cycle. And so if you go all the way down to the bottom to cycle 24, they're significantly narrowed, the probability distribution. And in cycle 24, for DST, we don't see anything up, above minus 240 or something. There's not any very large storms, and there's many less hours even at smaller storms. And on the right-hand side in AE, you can see that it's also narrowed significantly, but not as much. So it has affected the amount of magnetic activity we're seeing that will affect many processes that are going on in geospace. So next slide. Next slide.
We are on the next slide. Is it advancing on your end?
No.
Oh.
Oh, there it goes. I see it. Okay, I see it. All right. So it's interesting, the properties of the coronal holes and how that translates down into what happens in geospace. And so, there was a very big difference in the coronal hole patterns and sizes between 22 and 23. And in 23, there were many times four coronal holes at the same time, rotating around. And it gave a really nice fingerprint of 6 to 7 day periodicity for the four streams. And in a lot of parameters in geospace, 6 to 7 day periodicity showed up, and 9 day periodicity, 13.5 and 27. And none of the minima preceding the 23-24 minima actually showed 9 and 6.7 day geomagnetic activity occurrence in the AA index and in other parameters. And so it gives you a really neat way to see how deep do the high-speed stream influences go into the atmosphere. And it was kind of surprising how deep they came. They descended those influences all the way down into the noctilucent clouds and ozone and many other interesting things. And I know people are going to talk about solar cycle 24, and I'm very interested to see how it's developing compared to this. Next slide. So the properties of high-speed streams, I wanted to go over them just really quickly. These are from Bruce Girottani. That you can see his plot on the left-hand side there of what the parameters basically look like in a high-speed stream that's hitting the Earth. So you have the important thing I want to point out here, you have the velocity pickup, and to be a high-speed stream, it needs to be 500 kilometers a second or higher. And you have a lot of alpha wave activity in the B, in the CIR, and then extending for many days after. So it drives a lot of auroral activity and very little DST. The storm size is very small. It's usually below minus 30, above minus 30. But the activity, the alpha waves are driving a lot of auroral activity. And then there's a question of what is that exactly? Is it substorms that are being driven? And you can see these three pictures here taken from another paper by Girottani that show what it looks like in the auroral oval when you have a storm, what it looks like when you have a substorm, and then what it looks like when you have these auroral activities being driven by these high-speed streams called Hilka events. And so it's very much more global than a substorm, and there's been debate about what it actually is. Next slide. Okay, so this is how the high-speed streams are being plotted here. I know Janet Lumen showed some of these plots yesterday. It's pretty cool that you take and you stack up Carrington rotations or Bartle's rotations And so you can see when you look at this, how wide each of these features is tells you how many days it lasted, and how tall it is basically tells you how many Carrington rotations it existed over. And so you can see that in the last solar cycle, you can also see these pink lines coming across that are separating the solar cycles. So in 23, you had a lot of high-speed stream activity and was really strong. And you can see that all in these different periods where the high-speed streams are coming through over and over again. And then as you go into solar cycle 24, the activity died down, but in 2015, it popped up again. The coronal hole areas very abruptly increased. And it was, immediately the signatures are in the, the speed and the how long the high-speed streams are lasting as you go above 2015. And a lot of interesting, that triggered a lot of interesting things in geospace, that abrupt change in the size of the coronal holes. And this other plot here just shows, histogram of the number of high-speed streams in cycle 23 and 24. And in 2003 really was the most energy pumped into geospace from the high-speed streams. And you can see in solar cycle 24, at 2015, you can see this abrupt shift in how many high-speed streams are coming through. Next slide. Okay, and here, this is the radiation belts in the bottom there, the bottom panel there, from 1993 all the way up to 2017. And you can see there's right above it, there's sunspot numbers, and there's the solar wind speed in the red. Above that, there's the DST, the minimum minus the maximum minus the minimum of DST. And then above that goes electrons at greater than 2 MeV. And so you can see one thing you can see right away is that wherever you have these spikes in DST, these are the places where the radiation belts, the particles get injected pretty deep. And you can, they can even go into the inner region. Up in the corner is a plot of the low latitude coronal holes in orange and the polar coronal holes in blue. And you can see right at around 2015, there's an abrupt increase in the size of the coronal holes that kind of lasts after that for the rest of the solar cycle. And so you find that if you go back down to the radiation belt plots, that black dashed line, that shows you where that abrupt change in the coronal hole sizes showed up, and you have an abrupt change in the radiation belts there as well.
Can you wrap up
Next
in
slide.
a couple of minutes, please, Janet? A couple minutes.
Okay, thank you. Next slide. Okay, I'm going to skip this one since we only have a few more minutes. I think it's really, really interesting that the co-rotating interaction regions actually have structures in them that will drive ULF wave activity at the Earth. Here's some interesting features that are showing up. We're getting rare electric blue auroras, which means we have N2, molecular N2 plus at high altitude in the atmosphere. And that's interesting. It just abruptly started showing up in 2015. I'll show you a few interesting observations. We have new auroral forms showing up, the dunes there, that people are relating to neutral waves. That's a Bohr wave there, creating these structures in the aurora. And then on the bottom there, we have noctilucent clouds that are showing up at lower latitudes than usual. And these noctilucent clouds actually have in them signatures of the high-speed streams. Next slide. And you can see here, this is a blue air glow, these plots here, and an abrupt change in the amount of the air glow occurs at 2015, and where the coronal holes got larger. And in the bottom, you can see that 700 kilometers a second is a large amount of the emissions occurring there. Next slide. This shows the periodicities in the noctilucent clouds in the polar mesospheric summer echoes. And in the interest of time, I really want to get to the last one. It does show that there are periodicities at 90 kilometers, 80 kilometers that line up with the 7 and 9 day periodicities in the high-speed streams, which is really interesting because we never thought the effects would go that low. Next slide. And we're seeing noctilucent clouds going far below where they're normally seen. And over here, you see there are noctilucent cloud sightings in northern summer in all of those years, all the way down to 2019. So there's been an abrupt change in where you see noctilucent clouds now. And is that related to this weak cycle? And one more slide, I think. Next slide. Oops, keep going. Next slide. And then the last interesting thing is that if you look over at that stack of plots there, the top plot gives you the number of high-speed streams. Below that is the descending NOx that's moving down into the polar vortex to interact with ozone. And you can see that the peaks in the descending NOx in the southern hemisphere are lining up with the high-speed stream activity. And then in the northern hemisphere, however, you can get descending NOx when there isn't a lot of NOx, auroral NOx being produced. And it has to do with the very, very strong polar vortex that develops. So there's a combination of meteorology and high-speed stream inputs. And the reason it's so important is if you look over at this figure on the far left, when you have, you need to get the NOx descending over the polar vortex. If you have a very large storm, the NOx goes equatorward of the polar vortex and it gets lost. It's not descending into the polar vortex. If you have sort of a modest kind of a auroral activity like you would in a high-speed stream, then it gets deposited, the auroral oval is much smaller, it gets deposited into the area where it can easily be drawn down into the polar vortex. So the size of the storm is, the more NOx you get is related more to a moderate sized storm because then most of the NOx goes into the polar vortex. And the last slide is my summary. So here's the focus is on the continuing decrease in energy that's entering geospace. It decreases all the magnetic activity and it has implications for the structure of the ITM. Coronal holes, high-speed streams and geospace linkages. Solar wind periodicities tell us how deeply the activity is penetrating into the atmosphere, which was surprising, how deep some of it went down into the mesosphere. The radiation belts, I forgot to point that out, they haven't penetrated below L of 2.6 since 2005 because of the strength and duration of the streams. And that may be the explanation for this impenetrable barrier, or part of the explanation for this impenetrable barrier that was referred to, that the radiation belts don't go below a certain L value because of their interaction with the plasmasphere or with radio waves from, human-induced. Blue auroras imply that there's high-altitude molecular ions, and the EPOP spacecraft has been observing the more frequently than expected these molecular ions at high altitudes. And the blue auroras popped up more strongly when the coronal hole area is increased. So the connection between that is an interesting issue. There's the appearance of unusual auroral forms, which links to neutral waves. Noctilucent clouds have 7 and 9 day periodicity in them. And they're at 80 kilometers, and they're now appearing at unusually low latitudes, and we don't know the reason for that. And auroral NOx and ozone loss in the upper stratosphere is linked to high-speed streams and also to the meteorology of the polar vortex.
Thank
So
you
all of
so
these things
much.
are,
Thank you so much, Janet. We're running a little
you.
late, so we need to move on. I remind everybody, put your questions into Slido, and we will have a full discussion section after the break. So we now need to move on to the next speaker, who is Christina Lee. Looks like she's ready to go. Would you please share your slides and tell us all about solar activity throughout the heliosphere, the impacts and effects of solar eruptive events on planets in the inner heliosphere.
Oh, she says she can't unmute.
And
Yeah.
you will need to unmute Christina.
She said she can't.
She can't?
That's
Okay, I'm
she-
working on that. Christina, you're now a co-host. You should be able to.
Try again. Yes.
Can you hear me now?
We can.
Okay, good. I wasn't sure about co-host initially, so okay. Can you see my screen?
We can see it. Go to full screen
Okay, move in
mode.
presentation mode. And can you see it in presentation mode?
Perfect. Take it away.
Okay. All right. Hello, everybody. I'm going to cover the P part in WHPI and talk about impacts and effects of solar eruptive events and quiescent solar periods on the planets in the inner heliosphere. So I'm going to work my way from Mars, which is what I'm very familiar with, to Venus, then to Mercury. And I'd like to thank all the co-authors here, especially the top row co-authors who contribute material to this presentation. And I apologize if I'm talking too fast. You can shout out if I do. I'm trying to cover a lot of stuff before we go on break. Okay, so let's see, my slides advancing. Here we go. Okay, so starting with Mars. We've been making continuous observations of space weather effects and impacts at Mars for over 2 solar cycles now, starting with Mars Global Surveyor mission, then Mars Odyssey, Mars Express, and MAVEN. That is, and some of these are still making measurements right now at Mars. Some of the measurements that have been made so far are, for example, solar energetic particles, observations made since 1997, starting with Mars Global Surveyor, and also Mars Express. And these missions, they measure SCPs as penetrating background counts, so not direct measurements, but nevertheless, these are measurements that we have in hand. And of course, Mars Global Surveyor doesn't directly measure the IMF or dynamic pressure, but there are proxy measurements from this mission. So we have these observations that started from 1997. And of course, some of you know about the MAVEN mission. MAVEN is making direct upstream observations. So that's what I'm showing here on the right-hand side. And also solar EUV observations. There's an EUV monitor on MAVEN. So I know some of you have heard of these observations before, and I'm not going to give you details about it. I just want to give you a heads up in case for those who don't know about them. Okay, let me now get into the impacts and effects of the space weather event at Mars. Okay, so first of all, Mars does not have a global magnetic field. It has an induced magnetosphere, and these are strongly perturbed by crustal magnetic fields in the southern hemisphere of the planet. And there's also an ionosphere reservoir. Now, because there's no global magnetic field, the planet is only weakly shielded from impacts from space weather events. Okay, so some of the disturbance that we see so far are from CMEs and CIRs on the magnetosphere. So for example, there's been observations of compression of the magnetopause observed by Mars Express during a CME event. So you can see there's a boundary. These are observations of the boundary layer. It says altitude versus time. And then when the CME event followed by fast ring event occurs, you can see compression. So things are pushed down before it relaxes back out. On the right-hand side, showing MAVEN observations, in particular, the magnetospheric disturbance index, MDI, developed by Jacob Grusbeck et al. And basically, this is showing that when there are CME events and also CRR, SIR events, there's compression in the magnetosphere. Okay, now I'm going to segue to auroras. So in particular, discrete aurora that's been observed, for example, first by Mars Express. So on the left-hand side, showing Mars Express observations flying over the crustal magnetic field regions in the south of the planet where to observe these discrete aurora, and they're due to accelerating electrons that were observed by Mars Global Surveyor. So I'm showing profiles here on the right-hand side. And these events, they found that they tend to occur, although not always, but they tend to occur when there were SEP events. So that's really interesting, and this is an ongoing topic of study by the community. Still fully understand why we see discrete aurora and why don't we see them every single time when we have SEP events. There's also diffuse aurora, which is a global phenomenon at Mars. This was first observed by MAVEN. So you can see a diffuse aurora on the right-hand side, taken by the IUVS instrument on board MAVEN. And this coincides with high flux SEP electron events. Okay, now there's also effects, of course, by solar flares. And these affect the ionosphere and the thermosphere of Mars. On the left-hand side, I'm showing altitude profiles of electron densities in the ionosphere. You can see the profiles for when there's no solar flare event versus when there is a solar flare event, shown in the red profiles here. These are observed by Mars Global Surveyor. On the right-hand side, I'm showing an example of increase in temperature in the thermosphere when there's a solar flare event observed by MAVEN. This is actually during the September 2017 solar eruptive event period. All right. Jumping into atmospheric escape. This is a hot topic in the Mars community because everyone wants to know where did the water go and how did atmospheric escape play a role in the disappearance of the water. And so when there's extreme solar events, the atmospheric escape rates can really increase by orders of magnitude. So for example, Mars Express have observed during a CME event period, an increase in the flux by several orders of magnitude when there's a CME event. So you see the colors going from blue to red. On the right-hand side, I show Mars Express observations of increase in escape, also during CIR, SIR events. So you can see a bit of more red, higher fluxes of escape versus non-CIR periods. Okay. Finally, MAVEN observations. MAVEN have also observed escape in ion and neutral particles. So the top right-hand side shows basically there's a 5 times increase in the neutral escape when there's a CME event, and this is these are the data from these are the escape rates due to this September CME event period that I mentioned earlier. On the bottom shows the 20-time increase in the ion escape from the same CME event. So that's really interesting. Okay, that went by really fast, and I'm going to unfortunately have to segue to Venus now. Okay, impacts on Venus. I'm skipping Earth. Janet talked a bit about Earth earlier with high-speed streams, and I'm not going to go into Earth at all. So Venus. Okay, there's been fewer observations made of Venus on space weather activity and impacts on the planet, starting with Pioneer Venus Orbiter, which was in orbit since 1978, and then it ended in the early 90s. And then we also have Venus Express. Of course, we're taking advantage of the mission flybys right now around this planet. So, for example, Venus flyby from Parker Solar Probe, from Solar Orbiter, and also Bepi Colombo, which is I think happening soon, if not already passed. And these flyby missions will add a lot more information to our knowledge about impacts of space weather activity at this planet. Okay, Pioneer Venus Orbiter and Venus Express measured many of the basic properties of the induced magnetosphere of Venus. So like Mars, Venus does not have a global magnetic field, has an induced magnetosphere and a very thick ionosphere. And these two missions, they study how the interplanetary conditions affect the ionosphere and, of course, affect the atmosphere escape. The PVO radio occultation in situ measurements show the ionosphere response to increasing solar wind pressure, nominally basically the lowering of the ionopause and ionosphere magnetization. So on the bottom left, showing the PVO altitude profiles of electron density, showing the response to high pressure events. Right-hand side, Venus Express observations showing similar profiles in response of the ionosphere in response to high pressure events. And of course, there's also escape of oxygen ions. PVO made this first observation and suggested that high pressure enhancement from CMEs causes the oxygen ion escape. So you can see the profiles here when there's a CME arrivals in the shown in the black solid lines here. And you can see the points of oxygen flux is increasing when there is a CME arrival. The right-hand side shows Venus Express observations for during a CIR or ICME event. You can see the increase in oxygen flux escape, basically, versus when there was no CIR or CME event. Okay, Venus, we also see aurora. In this case, I'm showing the diffuse aurora on the night side. So day side is marked by the dark crescent here. And so in previous orbit, you don't see any diffuse aurora, but then you start seeing these patches here indicating diffuse aurora. This is observed by PVO, and these are due to electron precipitation. Venus also has green line emissions. So this is a pretty hot topic and very exciting topic, I think. These have been detected from ground-based observations. And so, for example, on the left-hand side, you can see the green line emission at Venus during a CME event. And you can see in the middle panel, weaker emissions that are associated with more quiescent solar wind periods, in this case, maybe a CIR. And Sarah Kovac and her team, they're actively studying the causes of the green line emissions, particularly during calm, quiet solar wind periods. And so they're taking advantage of the Venus flybys from Parker Solar Probe observations of the flybys, together with modeling of the solar wind parameters from the WSA model. And so that's what I'm showing here. So some of the WSA predictions of the flyby overplotted with Parker Solar Probe. And you can see that during the flyby number 3 in July 2020, there was some evidence of green line emission at Venus. And the question is, what's causing them? Because there's no CME event. And Sarah and her team, they're working hard to find correlations. And they think there is a correlation with the Hughes current sheet crossing together with the observation of the green line emissions. Okay, finally, Mercury. So there's even fewer observations at this planet. Mainly there's the messenger observations, and these occurred during the peak of the solar cycle 24. And soon there will be Bepi Colombo, which is slated to arrive to the planet in 2025. So Bepi Colombo will provide a lot more opportunity to study more comprehensively impacts and effects of space weather at this planet. Okay, so first of all, Mercury has a global magnetic field and it has an intrinsic magnetosphere. And this magnetosphere experiences very extreme solar wind forcing because Mercury is very close to the sun. And so I'm showing some observations from MESSENGER where you can see, for example, the BZ component. You can see the smooth rotation. And this is evidence of the day-side magnetosphere right here before the magnetopause crossing that's marked by the vertical dashed red line. And the induction currents can increase Mercury's total magnetic field moment by up to 25%, okay? Now, competing with this are the magnetopause reconnection process. This occurs at very high rates to erode the day-side magnetosphere. And so you can again see from the BZ component, it goes from negative to positive, indicating the day-side magnetosphere. You can see a lot of high fluctuations indicating the magnetic reconnection processes. Now, when with the tug-of-war processes between the induction effects and the magnetic reconnection, you can actually erode the day-side magnetosphere to the point where it disappears. And so, again, looking at the BZ component in this panel here, you can see that the BZ is negative, and it doesn't ever go back positive when it crosses the magnetopause. And I thought this is a really nice illustration by Reka Winslow and her co-authors showing this. Okay, so the thin line seen here, so in particular the BZ, which is shown in blue, you can see again the smooth rotation before a CME event. Okay, and when it goes back up and goes positive, that's an indication of the day-side magnetosphere. But when there's a CME event, so this is the thick wiggly lines, you can notice that there are no thick wiggly lines on the left-hand side when it, before the magnetopause crossing. That's because the day side disappeared. So that's really interesting. That's really cool. So the disappearing magnetosphere day side events, what that means is that the solar wind is having direct access to the surface, and because Mercury is no longer protected by its global magnetic field. And so this actually creates an interesting scenario where Mercury becomes Mars-like, as Jean DeBrasher has pointed out in previous talks that she has given. And so I think that's really cool. Okay, concluding remarks. This is a very quick overview. I apologize, I'm speaking too fast, but there's a lot to cover. And I obviously didn't include any discussion about the outer planets, which, you know, Fran and I think on this workshop, they are very familiar with. You know, because all of these planets, they interact with the planetary environment and only cover a very small snippet of the interactions of the inner planets, okay? But the bottom line is that, you know, space weather events and the interplanetary conditions, they impact each planet in a different way depending on the characteristics of the planet, whether it has an intrinsic or induced magnetosphere, what are the characteristics of the planet's atmosphere and ionosphere, and of course, how far away from the sun is it? And what I wanted to segue to, and this is my last final point, are, you know, the observations from planetary missions, they contribute to a larger heliospheric data set, which is, I think, you know, why the P part in a way exists for WHPI now. You know, for example, measurements from planetary missions like Mars, they've been used to study the influence impact by common space weather events. So, for example, September 2017 event, to look at impacts and effects at different planetary locations. Okay, so, you know, at Earth and at Stereo A, for example. Rega Winslow and her team, they've utilized observations from Mercury, Earth, and Mars to study the propagation of CMEs from the sun out to these distances, and also how do the forebush decreases, the features associated with CMEs, how do they get affected as the CME propagates outward? And finally, you know, the observations from planetary missions, you know, they can be used to better constrain solar wind models like WSA and LIL, and also SEP models, just like STEPMOD from Janet Lumen. So that's all I want to say. I apologize again that I'm talking so fast, but I want to cover a lot, especially for a break. So thank you for your attention.
Well, thank you so much, Christina, for getting us back on time. This is really an excellent overview. We've had a lot of material presented to us this morning. I think there've been some questions in Slido, and Slido remains open, and please do put your comments and questions there. We are going to have a discussion. We're going to have a break first, and then we're going to come back and have an hour-long discussion in session 66, where we're going to have chaired by Robert Allen and Ryan McGranahan, and we'll have all of the discussions and presentations. I hope that the speakers will stay on for that discussion session in 15 minutes, because I know there's a lot of questions for them, and we'll be going through those questions and having a discussion. And after all, this is a workshop, and the whole point of that is to have extensive discussion. So this has been a really fabulous session. Unless my co-chair Noor has anything to add.
As you mentioned, Fran, we have really a very good number of very interesting questions, but please keep your question coming. We have a long discussion, and I'm pretty sure we're going to learn a lot from this open discussion between the speakers and the audience.
Thank you. Catherine, do you have something to add?
No, I was just going to mention that I posted in chat the link to Slido for questions, and that we will return from break at 45 minutes after the hour.
Okay. And so I think with that, I'm going to thank all the speakers and the contributions that everybody has made. And this was a really fascinating session to get us up to speed. And take a break. I'll see you all in 15 minutes. Thanks. Bye.
Great. So welcome back, everyone. So to get started with, one of the highest voted questions on Slido was from Carlos towards Dave. So the question was, is there any reason why there's the relationship between the AA index and sunspot area is not linear for large AA? Instead, it seemed asymptotic. And so I'm not sure, Carlos, did you want to elaborate on that any, or do you want to go ahead and let David answer?
I think Carlo is just rejoining us. Let me just make him a co-host.
Okay. And again, if you have other questions, feel free to raise your hand.
Yes. Hi. I don't know. I just logged in. Basically, this is related to that plot that show that the relationship you said they was linear, but if you look carefully, it seems like it's increasing, but like kind of asymptotically getting flat. I don't know if there is any physical reasoning just to say that it's not linear and it could be flat.
It does look like it might roll off at high AA index, but I think a lot of that is because cycle 19. If you take cycle 19 out of there, it looks like a very linear relationship. So it's unclear. We need another really big cycle.
Mm-hmm. Okay.
So Dave, one question I have with that is for the AA index, because I'm not as familiar with that one, where are those magnetometers located? Because I know we do see kind of asymptotic behavior, talk about like polar cap potentials and things like that.
There's a site in England and a site in Australia. The site in England at least has moved once, if not twice. So again, they're designed to be antipodal, one on the northern hemisphere, one on the southern hemisphere at the same magnetic latitude. And the nice thing is, again, it goes back to 1868.
Mm-hmm. All right, and so still staying with Dave, see the next question we have is, very nice talk, Dave, thanks. In your 3-point plots, so it's the solar cycles 22, 23, and 24, you show some interesting linear trends. Have you got similar polar plots for coronal hole size versus at minima versus the following maxima?
I have not. Certainly, it would be interesting, but no, I have not.
Okay, thanks, Ryan. So the next question is from Noor. So Noor, do you want to go ahead and ask your question?
Sure. Hi, David, and hi, everybody. Well, this question is basically looking forward a little bit into the future, in particular that in a couple of years, we will have the decadal survey. We will also have the HALEU 2050 vision. And what we are looking at is probably big steps forward in our knowledge and heliophysics in general. But the question was mainly about the solar dynamo. And there are a few puzzles there that we cannot solve with the data we have now. And my question to David, and probably to anybody out there who wants to comment, what type of missions that we really need to make substantial advances on this topic?
Certainly, solar orbiter will help a lot. Looking at the poles, a better look at the poles is fairly instrumental. In particular, trying to do helioseismology near the poles, so you can see what the flows are like as a function of depth. It's very hard to do from Earth viewpoint, but over the poles, that would help a lot. You know, anything that tells us more about the internal flows, and even better yet, the internal magnetic field. I still am not convinced we know what the field configuration is in the interior of the sun throughout the whole solar cycle. So it'd be anything we can add to that would help.
I agree, David, that solar orbiter will help quite a bit. But do you think with the limited time we have for the remote sensing in particular, above the to look at the poles, do you think that will be sufficient to probably elucidate the major questions we have there?
I do. I think even with limited time, knowing, you know, at a moment of time what the meridional flow is a function of depth at high latitudes would be quite helpful.
Okay.
Can I make a quick comment on that? I absolutely agree, but there is an issue with helioseismology that you need a certain amount of integration time to beat down noise. So there is an issue of getting sustained views from high enough latitudes is a challenge, which I think is crucial for the next decade.
So Sarah, what do you think? What type of missions do we need?
I think we need missions that will go up above 75 degrees and stay up there for several months. But that's me.
All right, so I see our next question is from Sarah. So Sarah, while you're here, do you want to ask your question to Dave?
Absolutely. Yeah. So this is a question, it's kind of the one that I keep coming back to. I'm trying to understand the weaker, we're seeing this, that plot that, as you said, could launch 1,000 papers. The weaker polar field, the weaker dipole, the weaker, Janet showed us the IMF going weaker. We saw it, Pete's talk yesterday, we saw these trends. But I'm trying to understand also what we expect to see in terms of the coronal structure and in terms of the dipolar structure versus the more fuzzy, diffuse streamer belt. This could be related to the heliospheric current sheet tilt, but I'm not totally sure because it's more about, and I'm wondering if it's maybe about a ratio of global poloidal to global toroidal fields and how that changes at minimum. I wonder if you could comment on that, David.
Yeah, I think during this last minimum, we saw cycle 24 continue to produce active regions well into it, which will add more than the toroidal part. So again, I think there's more of an overlap during this cycle, which ought to make it a little different than the cycle 23-24 minimum. I don't know whether that helps you or not. I haven't looked at the heliospheric current sheet tilt. I thought we were told not to look at that.
Were we? Sorry. Why were we? Well, okay, so here's the thing. The tilt is one thing. And unfortunately, I just heard from Pete and he's not on. I kind of want to get Pete on this conversation, but if you have the pole weak compared to some of the higher order multiple field, you might have a more diffuse streamer belt without actually having it more tilted. If you have a large peanut for the elephant trunk, a large active region, that will impact the tilt of a heliospheric current sheet. But in 2009, for example, we had a very weak dipolar field. And we also didn't really have, and yet there are differences between that minimum and this one. And maybe there's others in the group who may want to comment on this, but I think there's more to it than just the dipole. I think it's relative to something else in terms of how the structure appears in the corona. Yeah.
Yiming?
Go ahead, Yiming.
Yeah, I commented about this yesterday. I think it all has to do with the remnant active regions. As I said, an active region for the flux to the part of the flux, the non-axisymmetric part, that's what determines the warping, tilting of the current sheet. And that takes about 1.5 years to decay. It depends on basically the meridional flow timescale, which is about 1.5 years. It transport flux from low latitudes to mid latitudes where it's annihilated by diffusion and rotational shearing. So you just have to look at the active regions that emerged close to minimum, and then, well, you can do a flux transport simulation and then see how long they take to decay, and if there's still some remnants at lower latitudes during your minimum, your current sheet won't be flat. There will be the dipole may be slightly tilted, but there will also be higher multiples, non-axisymmetric multiples. And that's why your streamer belt won't be completely flat. I don't think there's any mystery about it. It's very, in principle, it's very simple. But
Janet, I know you have your hand up.
Yeah, related to that is ubiquity of pseudostreamers. You got a big, thick pseudostreamer chunk around the middle of the sun related to the high order moments in these decayed active regions that are dominating polar fields. And so in my view, the whole picture is really altered by pseudostreamers. And the current sheet winds through pseudostreamers, but there's also a lot of stream interfaces that don't have current sheet, heliospheric current sheet association. We shouldn't disregard that structure, which is now very important, I think.
Yes, but Janet, the pseudo streamers, everything's a consequence of the active region flux that's left over. I mean, whether you have pseudo streamers or not, that depends on the what's the active region remnants. And actually, what's surprising to me is that the cycle 23, 24 minimum, there were a lot of active regions that emerged late in the cycle, like 2007 through 9, and they created high-speed streams. And yet 2009, just after that, it was the lowest minimum that, one of the lowest minimum ever. So, and I guess a similar thing happened in this minimum. There were quite a lot of high-speed streams, active region emerging very late in the cycle. But
real quick, I want to hear from, so Juliana, I know you've raised and lowered your hand a few times. Did you want to add something to this?
I have a question for Yiming, and I agree with you. Really need to model, because sometimes your intuition, it doesn't really capture the complexity of the sun. But we had some active region in the middle of the minimum for this cycle. So I was expecting, if anything, they should make the shape of the corona more complex, because we have this flux that was still there in 2018, and instead we're seeing more like the dipolar structure. So I'm not quite capturing what's going on, but I agree, you really need to simulate that. And as Janet was saying, there is a complexity that has to do with pseudo streamers and where the open flux is and all of that.
yeah, actually, I wanted to comment on in one of the talks, it was Janet's talk, Janet Koziris, and she said, oh, there were lots of high-speed streams towards the end of cycle 23, and then they went away, and then they suddenly came back in 2015, and it's well known that these recurrent high-speed streams occur at the declining phase of every cycle, every single cycle, and it's just due to the fact that late in the cycle, you have the activity, sunspot activity moves to low latitude. And that creates an equatorial dipole component. Basically, it tilts the dipole, although we shouldn't talk about tilted dipoles. And that basically tilts the polar coronal hole towards the ecliptic. And that's why we get those recurrent high-speed streams. And then when those low latitude active regions die, then the high speed streams die away.
So Sarah, I see you have your hand up. Did you want to?
Yeah, sorry, I thought I couldn't raise my hand as a co-host, but I can. Yay. I wanted to just make one more point, which is that there are two issues here. One is the tilt of, I mean, we don't have to think of it as a tilted dipole, but the thing that has to do with the heliospheric current sheet not being flat. Another one has to do with how broad it is. And in 2008, it was very tilted. There were low latitude coronal holes and high speed streams. In 2009, it was flat. The heliospheric current sheet was relatively flat, but the streamer belt was very, very wide compared to 1996. So in other words, you can have higher order multiples that are axisymmetric. And do you think, Yiming, that these are also part of remnants of decayed active region flux?
Yeah. Well, yeah, I think so. If they're non-axisymmetric, then that's decayed flux.
Okay, but you can also have axisymmetric, so the border, the dipole versus the octopole or the quadrupole. Oh, well, not the quadrupole.
Yeah, well, the axisymmetric ones are like the polar fields, and the polar fields are extremely concentrated, and that means that you need more than just the axisymmetric dipole. You need L equals 3, L equals 5, L equals 7, 9, so on. And that concentrates the polar fields, but they're axisymmetric. So I think it's mainly the non-axisymmetric multiples that matter for the, making the streamer belt not flat. Okay, one interesting thing is so sometimes we observe more, the tilted dipole would predict 2 high-speed streams per rotation. But Janet mentioned there were sometimes 3 high-speed streams, sometimes 1 and 3. And I think that requires the presence of more than just a dipole. That requires like quadrupole as well. So, but it's very difficult to predict exactly how many streams we can see.
So with that, we're going to move to the next question. So this one's to Janet. So Mary Hudson, did you want to raise your hand and ask your question? Or I think you can actually just unmute yourself.
Yeah, okay, I unmuted myself and now I have to see my question, which requires going to another screen. You know, oh, there I am.
Oh.
Good, thank you. I got it. Okay, thank you.
Okay.
Janet mentioned 6 to 7 day periodicity in coronal holes. Janet Kazir, about 7 to 9 day in atmospheric response. And so I was curious about this difference. And I see a couple of other people were.
I can't unmute.
Okay, Janet, let me see if I can find you here. Okay, I just sent you a request to unmute. You should be able to unmute now. Janet, are you there? Yeah, it seems that she might be having a slight delay issue on her end, on her laptop.
I could say something.
Yeah, go ahead, Carlos.
Yeah, I think you see there 6-7 and the other 7-9. I think it's very close. I don't think it's anything physically significant between the 2 periodicities. In anything, it's like a week-long period. I don't know.
Okay, yeah, I don't know. Yeah, I don't know if Janet can get on or if Barbara Emery's on and would comment. But at any rate, I was interested if there was, you know, I would have expected it to be the same, like you say.
Okay, I'm unmuted finally. Yeah, what Carlos was saying was correct. I mean, if you have 4 high-speed streams in the rotation, in a 27-day rotation, then the periodicity is 6.75, and then the next periodicity would be 9 if you had 3. So the 6 to 7 is really the 6.75 or however it shows up in the periodogram. So if it's really close. So, I mean, that's just why that was listed like that. Sorry for the confusion.
Janet Lumen, your hand is still up. I'm not sure if it's just from earlier or if you had something to add here.
No, I had another question for Janet Kazira, but not the same topic.
Well, go ahead while your hand is raised.
Okay, for Janet Kazira, hi Janet. I was wondering about preconditioning of the geospace system by this long period of low solar activity and what role that may play in all these odd things that are happening.
I think that is a great question that does not yet have an answer. I know that when you're absolutely right that whatever the environment is that you introduce some feature in will interact with that feature and change what's going on. And I know, for example, that if you, when they do models of a storm, if they have all the same input parameters, but one has high F10.7, one has low, then the low F10.7 storm will have a larger temperature change, and it will it will penetrate to lower altitudes. So it's really important, you know, what you're introducing these geospace activity into, or and so I think you're right on with that. I mean, and we don't know. So, you know, you have a lot of molecular ions now at high altitude, and I don't know if it's just now or if it was there before, or because EPOP is seeing it. And so we got N2+ up there that's creating these, blue auroras that people comment on, that they've been watching the sky for 20 years and this is the first time they've seen this, and so on, that bright. So, I mean, I think you're absolutely right. We don't know, and that's a really interesting mystery that hopefully some of the new missions that are up there, ICON and GOLD, and future missions are really going to be able to start answering.
Right. Thanks.
All right, so our next question is from Ling. Ling, do you want to unmute yourself and ask your question?
Okay, sure. So this question is for Janet. So Janet, you mentioned that during the recent weaker solar cycle, the noctilucent clouds was observed in mid-latitude instead of high latitude. So I know that noctilucent was produced based on two things. I think it's the amount of water vapor and the temperature. So how is this related to the weaker solar cycle? What are the causes?
Yeah, I mean, that's actually also a really good question. I mean, observers are seeing these noctilucent clouds at very low latitudes, Paris, all over the place. And recently, there was a study done that verified that there was an increase in frequency of the, sightings of these noctilucent clouds. The reason is not clear. And as you say, I mean, if there's more water vapor, there's more water being introduced at those altitudes in the mesosphere. If there's more nuclei for the water to condense on, if the temperatures are colder, it might move things to lower latitudes, but also transport. And some of these features may be rocket launch noctilucent clouds that once they're produced, they were transported to the polar regions pretty fast, one or the other polar region, and they create really bright clouds in those regions. And, so they're transported through mid-latitudes. And the question, so all of those questions come up. And is it related to the fact that, it's a weaker cycle, or maybe the temperatures are colder because the upper atmosphere is cooling all this time. It's in the summer polar regions. So I don't think that question is answered, and it's a puzzle. And it's actually been introduced to us by sky watchers. We wouldn't be able to observe it because the AIM spacecraft basically is concentrating above 60 degrees, where they usually see the clouds. So, I mean, interesting question.
Mm-hmm. Yeah, okay, thanks.
So our next question is from Anonymous. So bridging from the sun to geospace, Janet, how is the tilt/variation of the heliospheric current sheet observed in geospace? And could geospace be a sensor for these solar variations?
Okay, I'm going to have to phone a friend because like Sarah, I think that, this has to do with low latitude coronal holes or that persist, or you were just speaking about that, Sarah, right? I'm throwing this one to you.
Sure. Yeah, no, I mean, I think clearly the question, sort of thing that Yiming was talking about as well, about the structure that's there that's non-axisymmetric is going to affect at the sun, whether you have the low latitude open flux, which is then able to intersect the Earth and drive the high-speed streams. So I think in that sense, absolutely, geospace is a sensor of the solar variations. And what we're seeing at the geomagnetic indices that are related not necessarily to the CMEs, but to the CIRs and to the high-speed streams, that is geospace diagnosing the asymmetries back at the sun. Does that answer the question?
If whoever answered this question would like to follow up, please raise your hand. In that case, I think it might have answered the question. So, all right, so the next question we have is from Sarah. So Sarah, do you want to ask your question to Christina?
Yeah, and this is just a naive question, but I'd love to hear a little bit more from Christina. That's so fascinating to see the different planets and their different types of magnetospheres, and some of them were induced and some of them were sort of patchy. But globally speaking, this is, as I said, a naive question. What's the north, what's the south overall? So if you had a big BZ negative storm that was going to be huge at the Earth, would it be huge a lot of these planets, or?
Oh my gosh, it's been so long since I've taken my planetary science classes. Okay. I know that Mercury and Earth, I think their dipole fields are aligned the same, similar orientations. So I think the effects would be very similar. Mars and Venus, they don't have a global magnetic field, so the BZ doesn't really play an important role, I think, on impacts and effects at those two planets. Jupiter, Saturn, and all the outer planets, I think their magnetospheres are oriented oppositely of Mercury and Earth. And I think what was it, Uranus is like a super tilted, so it's like sideways. So to answer your question, I think the response at the outer planets will be different than Earth and Mercury, but I think someone like Fran or even Janet or Gina DeBraccia and other folks on this in this workshop, they will know how to better answer that question.
Yeah, Gina's hand is raised. So Gina, do you want to unmute yourself?
Yes, thank you. Well, Christina, your remembering of your planetary class was correct with all the directions that you were saying. So totally, Mercury and Earth are the same direction. The one thing that's really interesting about Mercury is it's not as dependent on the BZ component as a planet like Earth is. The IMF is so strong in the inner heliosphere at Mercury's orbit that in fact we find the direction doesn't matter as much for reconnection to occur on the dayside magnetopause and drive some of these really intense signatures that Christina was showing. So, but a southern BZ has a very strong effect. So if you have a CME with that configuration at Mercury, it would really show a strong impact on the planet. And as Christina said, Jupiter and Saturn, the dipole is flipped the other way. So you really probably wouldn't see much for a southward IMF or CME impacting the planets there. Also because those magnetospheres are more internally driven. And then for the ice giants, for Uranus and Neptune, it's almost anybody's guess at this point, because as Christina said, their dipole orientation, they are offset and they are tilted, but the planet's rotation axis itself is also tilted. So for instance, at Uranus, it's really interesting because the planetary magnetosphere's dipole will be directed towards the sun for part of the Uranian year, but then as you rotate the planet around, at one point the dipole will actually be perpendicular, not pointed towards the sun. So the solar wind interaction there is crazy, but I actually believe that Dan Gershman will be talking about this a little more on Friday as well. But I think that might answer your question, Sarah.
Yes, absolutely. Thank you. It's quite a zoo. Quite a zoo.
I see, Ryan, you raised your hand. Did you want to add something to this?
Sure. Yeah, I'm really fascinated by the comment that Gina made about the kind of less important aspect of the direction of the IMF at the inner planets, just because it's so strong there. I'm wondering if you see some kind of distinction at Earth even. Is there some kind of knee in the distribution for how large the IMF magnitude needs to be, where it starts to overcome some of the direction importance? Do you see that at Earth at all?
That's a good question, Ryan. I don't know that anybody has ever reported on a critical value for that. And somebody here may know better than I do because I studied Mercury more closely than Earth. But the fact is reconnection really starts to, you can focus more on component magnetic reconnection rather than anti-parallel reconnection when the fields on either side of the reconnection region become closer in strength. So for instance, at Mercury, why we're able to get magnetic reconnection even for a northward IMF is because the IMF on either side of the magnetopause ends up being pretty comparable in magnitude. That obviously happens less often at Earth. So I would say we definitely see, you know, that component reconnection going on at Earth, which means you can have different IMF orientations, but it would happen more often when there is a stronger IMF. But I don't know what would drive
there's always
that. Yeah, what
always
critical value.
reconnection. I know Stephen Fuseli's in a lot of papers where for northward IMF, even you just get, you know, high latitude reconnection kind of northward of the cusps or forward of the cusps. And so I know that, I mean, you're always having reconnection. It's just a matter of, if you want to think of that quintessential southward IMF subsolar point reconnection, that's where southward's nice. But, you know, there's always going to be some area where you're going to have component reconnection occurring. Janet Lumen, I see you raise your hand. Do you want to add to this?
Sure. Those of us who remembered Jim Dungy's GRL appreciate that the Earth situation is really what they call a halfway rectifier as far as southward IMF is concerned. It's like a switch or a clutch where you engage the clutch of the whole magnetospheric convection with the southward IMF that has some reconnection near the subsolar point. So I think that the Earth is special in its sensitivity, perhaps, to that southward IMF, and the injection of the ring current is the big story in making the geomagnetic storm and all of its effects. Mercury, I think Gina can pipe in here, doesn't really have the necessary ingredients to make a big similar ring current injection that even engages the upper ionosphere during intensely southward periods. So I think the southward field is an Earth thing mainly. Also, we have to in the outer planets that, as Pete Riley said, because of the changes of solar wind parameters, the viscous interaction, the Kelvin-Helmholtz instability, and other things start becoming more important relative to the reconnection process in those outer planets, and also the internal mass loading. And Fran can also elaborate on that. So anyway, Earth half-wave rectifier responds to a southward IMF is, I think, a classical Earth thing to do. So that is what I have to contribute here. Thanks.
Okay, so your next question is from Dave Hathaway to Christina. So Dave, do you want to unmute yourself and ask your question?
Yeah, I was curious about the Jupiter decametric radiation that's been observed for a long time and whether it was sensitive at all to solar wind disturbances.
So that I actually don't know. I'm guessing no, but I think maybe Fran could say something about that.
Yeah, do you want me to?
I don't know.
Sure.
Go ahead.
I commented in the chat. The decametric emission comes close in near the Io-Taurus and the Aurora regions. It's pretty deep inside the magnetosphere. So the source regions are around distances of 6 to 10, maybe even 15 RJ. The size of the magnetosphere is 60 to 100 RJ of the magnetopause on the day side. So it's deeply buried, and so very little response to solar wind effects, but is responsive to changes in EO's production of material that fills up the magnetosphere and is the main source. So very limited effect on the decametric radiation.
Thank you, Fran. All right, so our next question is from Zubair. If you want to raise your hand, I'm going to unmute you and you can ask your question.
Hello. I'm audible?
Hi. Yeah, I can hear you.
Actually, my question is, can we estimate the rate of erosion process which is taking place from inner magnetosphere to the outer planetary magnetosphere, so that we can talk about the prediction of when the planet becomes fully eroded like we have several planets, it doesn't have mesosphere, and we used to say that it from the time it got eroded, and that's why it doesn't have mesosphere. So can we predict the erosion rate of the mesosphere, either in inner planetary domain or in outer planetary?
Could you elaborate on what you mean by erosion? I asked that question at Slido. What do you mean by erosion?
When I'm saying erosion, I mean to say the magnetic field of the planet got weakened with respect to the time. Like the erosion process happens with respect to the CME, and we know that CME got eroded its magnetic field. Is it also possible with respect to the planetary domain?
So is this kind of the difference between a compression versus erosion, where if you can compress a magnetosphere or you can erode it by actually having a lot of reconnection occur, kind of strip away those dayside field lines?
Yeah.
Well, the magnetosphere of Jupiter and also to some extent Saturn are very compressible. So they're very sensitive to compression, not so much to erosion because there's small scale intermittent reconnection on the outsides. Not so much the Dungy dynamo that Janet was talking about for Jupiter and Saturn. When you get out to Uranus and Neptune, we only have one flyby, so we know very little about those highly irregular, highly tilted magnetic fields. But there's likely to be there much more interaction and be more sensitive to the field direction and some level of reconnection. If you want to call that erosion, okay. But we need to go back to Uranus and Neptune. With a single flyby, you can tell very little.
Thank you.
Claudia, I see you had your hand up. Did you want to add to this question?
Yes, please. Thank you for your nice talks. And I'd like to ask you, I'm I work investigating ionosphere and space weather. And I'm especially interested in the periods of solar wind. And we noticed in our spectral analysis that there is a more visible or periods of 7 to 9 days in 2018. And in our studies for 2008 and 2018, this periods 7 to 9 is not so evident. They appear especially when during geomagnetic disturbed periods. Someone could help me to understand this difference. I'd like to know if we are right or wrong, because our next step is analyzing the ionospheric parameters associated with the solar and interplanetary parameters and indices. Thank you.
So I guess, yeah, does anyone of our speakers want to make a comment on this, or anyone else? All right, Janet Kazira.
Yeah, I think that's an interesting observation. I don't know what the coronal holes look like in 2018. I'm hoping to learn that from this, from this meeting, from the workshop. The periodicities in the coronal holes are due to the fact that you have a certain number of them and they keep coming around and smacking the Earth. I wonder what the same periodicities are in geomagnetic storms. Are there multiple active regions that are creating storms at the same time, as you rotate around? So I think that's interesting, but I don't have an answer for that. Anybody else?
I think briefly I saw Ian Richardson's hand come up.
Well, yeah, I was basically the coronal hole structure is changing with time. It's not fixed. So sometimes at Earth you'll get the you get say two or three or four streams depending on the coronal hole structure that is down at the latitude that is actually affecting the Earth. So that's all changing with time. So that's the underlying. Now, what's giving rise to that, of course, is another question, but that's a basic reason that the stream structure is changing due to the coronal hole structure is changing. And the gym activity tends to follow the high speed, the solar wind speed, basically. So that's going to also respond to the changing structure. I guess Barbara Emery may have given a talk I missed earlier on, but yeah, we looked at worked with her a few years ago. We wrote a paper looking at different periodicities and different phenomena in the magnetosphere, and you can very clearly see these this periodicity changing as the stream structure change. So that's a quick answer, I guess.
Yes, thank you.
Sarah, did you want to add to that?
Actually, I was going to see if Barbara Emery was around because I think she showed us some data on that. Is she online? We did have coronal holes, as I think Ian also commented, during this time period. There was a time period of several months, and Juliana also talked about this. There was a time period of several months where you had long-lived coronal holes, and there was periodic behavior associated with that. Then they kind of dissipated, and we had CMEs, and then we had one coronal hole that was Mr. T that Ian talked about that was there for several months with a recurrent high-speed stream. So in the end, it comes down to which ones last for how long. In 2008, there was an extremely long period of time with essentially 3 coronal holes that just kept hitting over and over again, so that the 9-day periodicity was super clear. But we're seeing similar behaviors, just not as crystal clear as the 2008, I would say. But if Ian or Barbara Emery were here, they could probably comment more.
Yes. Can I chime in? This is Mary. It certainly, you see the periodicity in the radiation belts in 2018, 2019 with the recurring, coronal hole rotation. So I'll show that tomorrow.
Mm-hmm.
And I see, Marty, you have your hand raised. Did you want to add something to this? I think this will be the last comment on this thread.
Yeah, hi, thanks for that. Yeah, I just wanted to comment that we have seen these short-term periodicities, 13.5, 9, 6.5 days, all harmonics of the solar rotation period in the energy budget of the thermosphere. And we've looked at this now with time data for almost 20 years, and they really show up during solar minimum is when we see these. 2008 was that whole period around the deep solar minimum was very active in terms of these short-term periodicities in the high-speed streams. And so we've got a lot of this published. I don't know if we've got it updated to today, but if anyone's interested, I can certainly get plots for you of the occurrence of these high-speed stream events, which then cause the response that we see in the heat budget of the thermosphere at these 13.5, 6, and 9-day periods. So anyone would like to contact me on that, please feel free to, and I can send you the literature we have. And it's a very common feature, again, at solar minimum, at least that we see with the SABRE data and timed.
Great, thank you, Marty. So with that, we're going to turn the discussion back to some of the talks we had really early this morning, to back to what Barbara Thompson was talking about. And so to the discussion about virtual resources, the question we had was, what are the first few steps someone should take to start using the HSO Connect resources, such as the website, AWS Cloud, and GitHub? So Barbara, are you on to maybe answer this one?
Yeah. I think the first step is to I posted in that thing a form that's just sort of a general information form. It's a Google form, because what we're doing right now is we're trying to we want to get a couple dozen of these things accumulated before we finalize the interface. And so, we want people to be able to see, we want to make sure that everything is working well. And so we're glad that people are interested. We want a diversity of resources too. Lots of different types of resources so that, we don't make a decision that works for solar people, but not for planetary people, things like that. So the first step is to do that, or I can post the Google form in here as well. Let's see, I'll post that in the chat. And go ahead and fill it out, and you can resubmit it if you decide to update it, or you can also I'm posting the email address. This WHPI data models@gmail.com goes to a couple of us, and so that's if you email one of us, then we don't know what this person, heard or what they said or something. This way we can see the responses and we can make sure that everything's consistent. And then finally, what I'm going to be doing over the next, as we do these things, I'll be holding office hours. They'll be online. People can pop in. I got a question. Somebody's like, how do I use a Jupyter notebook? And I'm like, they're easier than you think. But it's easier. It's certainly easier if somebody sits with you while you do it. And so what I'll be doing is if anybody wants to enter something in the repository or the portal, if anybody wants to make something available on the cloud, if anybody wants to develop a resource to be able to access and manipulate that, we'll just have some office hours at different times of the day throughout the year so that people can make sure that they can do it easily. But first of all, either email us or fill out the form and make sure that we know you're there and are interested in putting things and getting access to this.
Great, and I think along this line, Nariaki also had a question. So Nariaki, if you wouldn't mind raising your hand, we can unmute you to ask your question.
No, I think Barbara already responded. So, I'm very slow accommodating myself to this new data analysis environment because I'm so heavily plagued by what is called the solar soft, which has been in existence for a quarter centuries. And with those things still available, it's very difficult for me to move into a different environment. So I just asked Barbara this question. So, but she answered. So I will take a look, but it can be fairly slow.
Yeah, and all of these, of course, a lot of these resources have been kind of developed for Python, but you don't have to be a Python programmer. They are right now. You can at least share things and provide access to things with a Jupyter notebook that has more explanation and things like that. It's a nice interface because you don't have to have Python experience to do that because they're interactive because they have markup areas too. They're not just code based. But we are trying to get in the cloud. We're trying to get an IDL. We're trying to get the IDL installed and then maybe an extension working so that we could even run IDL processes in the background. So when people are using the notebook, they could still be running IDL. That's a non-trivial thing, but we're trying to so that we can support people because I get it, Nariaki. There's some stuff I'm still doing wavelets in IDL. Nobody's giving me a good Python alternative, and I'm not going to be the one to do it. So, but I'll be but I did send Nariaki a link to a tutorial. I'll put it in the chat too. These are good tutorials to get you kind of started on understanding what a Jupyter notebook's about and how to develop.
Okay, thank you.
All right, so I see Ryan has the next question. So Ryan, do you want to unmute yourself?
Sure. Thanks for the presentation, Barbara. I think the website and everything are just excellent resources. I'm curious how or what you would suggest might be best practices for people to produce new things that build on these resources. So if they're doing the research, I think we all have the experience of producing something that's not usable even to ourselves a few months later. What would you hope for this community to kind of produce as part of their research that would feed back into this system?
Well, I think it's, again, I don't have a perfect solution. Like I said, we're still kind of evolving this, and I will rely on you, Ryan, heavily to help advise how to do this. But I think this is a great opportunity because, a lot of people, they either want to do something small or they want to do something so huge you can't get started. This is an excellent structure to build on, because we have people doing a variety of different things from different communities who have different experience and working in different environments, different languages and things. And so I think this is a nice structure that once we have that, we can build, we can start to understand if we can get this group working well together. Hopefully the cloud and the executable code on the cloud will provide this framework that we can build on and define that. But no, I don't have a solution. It's not an easy thing. But I hope that you guys are up to the challenge to help me, to help all of us.
I'll add to that. that this is such a perfect community to do this, because there will be people in this who are unfamiliar with producing usable resources. And as you're learning, if you can capture some of that knowledge of how you're learning to do that, that's invaluable to the community. And I think that's a really nice resource for it to come from. So I hope that this community can kind of think about how they're learning this along the way. So thanks for
an excellent point. Yeah, that's an excellent point. One of the things that we really want to take advantage of is if someone's already learned it, how do we make sure that other people benefit from not just that knowledge that they've gained, but also their path to that knowledge. And so, so hopefully we'll get good. That's what I like about the current sharing environment, is that it's not just that you're sharing the products and the code. They're expository. You get a way to explain and it kind of help people not have to go through the same thing that you went through. So thanks, Ryan. You're right. It's even more of an opportunity than I thought.
Thank you, Barbara. Robert, I wanted to ask you, there are a few kind of loose ends questions that we could bring up in the final few minutes here, but are there housekeeping items we need to do before the next session?
Maybe Sarah.
Not that I know of. I think we can keep going.
Great.
So before circling back to some of the more science questions, I wanted to give a chance for if anyone had any other questions regarding the kind of WSO Connect talks we heard, to raise your hands if you haven't had a chance to add them to Slido. And give a couple of seconds and then we'll move back to the science. Okay, so in that case, we'll go back to the science presentations. So Carlos had a question. Do you want to unmute yourself and ask yours to Christina?
Sure. So 2 questions. You showed some results from green line on Venus. So I was curious to know if those were measured with a spectrometer or how they were done. And the second question is, you're trying to relate that enhancement to Aurora. Could it be just like a regular background air glow that you don't need any kind of precipitation to see the enhancement?
Great question, Carlos. I hope you can hear me. So Sarah Kovac should answer these questions since she's the one leading the studies on the green line emission observations at Venus. Sarah?
So she is here, yeah. So
hi, yeah, so we have used the at Apache Point Observatory, there's a 3.5 meter with a spectrograph on it, and that's what we use to look at Venus. This is definitely an auroral feature. It is not an air glow feature. It is something that is only present during particular solar wind conditions. It is not an air glow. Candace Gray has a couple of papers on that. We've had lots of observations of Venus where the green line is not present during quiet solar wind conditions. So this is definitely a particle process that's happening in the atmosphere.
Okay, thank you.
Thanks, Sarah.
all right. So Ryan, if you want to progress to the next one. Okay, so the next question is from Juliana to Dave. So Juliana, do you want to unmute yourself?
Yes, I was curious about the cycle 19 being an outlier, if there is some kind of nonlinearity going on. And I think Dave replied that there is also a component due to the cycle 18. Dave?
Yeah, it's an cycle 19 is an outlier in how low the minimum was prior to cycle 19. And I think that's largely due to cycle 18. If you look at the data, cycle 18 just died a quick death. And, there was hardly any overlap. It didn't continue on to raise the level of activity during the minimum. So I think that's primarily why cycle 19 looks like an outlier when you look at the level of the minimum and sunspot number, or the level of the minimum and the AA index. Both of those are low, I believe, for that reason.
Great. So the next question is from Nariaki to Dave. Nariaki, do you want to raise your hand so we can unmute you again?
Yes. I think he already answered this question, but his most solar cycles are double peaked, right? And do the polar field measurements prior to the cycle indicate that kind of behavior? And his answer was something like 22 and 24. He looked at those things, but maybe he can answer the questions now.
I can answer it that we've looked at the hemispheric polar fields individually relative to the hemispheric sunspot area individually to see how well they were correlated, and they were properly correlated in cycles 22 and 24. As far as the one with the smaller polar fields had smaller sunspot area, but cycle 23 didn't pan out. They flipped the other way. In all three cases, they were small variations, and I think the bigger thing for the double peaks isn't so much size but timing. You know, when does one hemisphere come on versus the other, and we haven't really addressed that.
Okay.
So the next question is from Anonymous. So sunspot number during this last minimum is smaller than during the minimum in 2008, but other indices such as F10.7 not. It is slightly higher. Did you try to include other solar activity indices besides geometric activity indices such as AA for the prediction to the next maximum?
We used polar fields rather than the size of minimum. Use the polar fields at minimum to predict the next cycle. That seems to be the best indicator. So the others, the geomagnetic index, the AA index, of course, helps because it goes way back in time, but it just confirms the fact that you know these conditions related to the polar fields at minimum are the best predictors for the size of the next cycle. So the fact that 10.7 was a little higher, whereas sunspot number was a little lower, I don't think figures in so much.
Okay, thank you. So with that, we have time for one more question and then we'll go to a break. So how consistent is the WSO measurements of polar field from those of MDI before 24 and HMI number 25 when they're degraded with WSO resolution?
Lisa Upton and I kind of did that. We, in fact, the plot I showed in my talk showed both WSO, the Wilcox Solar Observatory axial dipole, and the dipole we got from assimilating data during MDI and HMI. And there are slight differences. I'm not sure how significant they are. And this was in the axial dipole rather than the polar fields. Polar fields, it's how do you integrate that makes it hard to directly compare, since WSO has just that single pixel going from 55 degrees to the pole. But you know, even with the axial dipole, there were slight differences. I don't think they're significant though.
Okay, thank you. So I was wrong, there's not a break. So now we're gonna head into the next session. So Juliana and Liang, we're handing off to y'all.
So, okay, welcome everyone. This is WHPI workshop session 7 on space age solar minima. And Juliana and I will be chairing this session. So this session is 1 hour long, and we have 3 presentations for the first 30 minutes, and question and answer and discussion for the second 30 minutes. And as usual, please ask your questions in Slido, and we will be address them together in the second 30 minutes. And Juliana will be moderating the Slido questions. So with that, so let's start the first presentation by Marty Malinczak from NASA Langley Research Center. And Marty, please take it away.
All right, I'm just trying to get my presentation here. There we go. All right, and let me go full screen here. Okay, it's in the middle. Okay, thank you, and it's great to be here and enjoyed all the conversations so far this morning. And I'm going to talk today about solar variability and impacts on the Earth's thermosphere during the space age. And this is largely and almost entirely from observations we made in the last 20 years from the SABRE instrument on the NASA TIME satellite. And I'd also like to acknowledge my co-author, Linda Hunt, who's been part of this work for about the past 15 years. So by way of introduction, we know that solar and geomagnetic variability strongly affect the thermal structure and density and composition of the thermosphere above 100 kilometers. And since the start of the space age, solar cycles have been generally decreasing in their intensity, and this has given us a resulting decrease in thermospheric temperature and density. And at the same time, though, CO2 has been increasing, and that also acts to reduce the thermosphere temperature and density. And so one of the questions we've asked, with having looked at this region now for onward of 20 years with time, is can we monitor the state of the global thermosphere in the absence of continual space-based observations? And I think the answer is yes. We've come up with a new index. We call it the Thermosphere Climate Index, to provide information on the global thermosphere energy balance and the budget and the overall thermal state of the atmosphere. And so it's an index that's derived from observations of the infrared radiative cooling of the thermosphere by nitric oxide made by SABRE on time. And it's a index that is composed of actual existing geomagnetic and solar indexes, in particular the F10.7 and the AP index. And so I'm going to explain to you how we've developed this index, and I'm going to show you its history over the last 75 years. So just to begin with some very basic concepts of thermospheric radiative cooling. This is the infrared energy that the thermosphere radiates back to space to reduce the kinetic temperature of the thermosphere. And there are three main mechanisms in this region of interest, which I'll call 100 to 300 kilometers altitude. You have nitric oxide at 5.3 microns, you have CO2 at 15 microns, and then the fine structure lines of atomic oxygen out at 63 microns. And the most temperature sensitive of all is the nitric oxide, because the energy level is so large, it's just very temperature sensitive. And so that's the one we're going to focus on in developing this thermosphere climate index. And taking a little bit more look at this, again, just to emphasize, when we talk about radiative cooling, it's the action of infrared radiation to reduce the kinetic temperature of the neutral atmosphere. And that's accomplished by collisions between atomic oxygen and nitric oxide. To initiate this process, you have a nitric oxide and an atomic oxygen colliding, and some of that energy is converted into the the fundamental vibrational mode of nitric oxide, removing kinetic energy from the atmosphere temporarily. And then there are two paths that can happen after that. The nitric oxide can radiate a photon of 5.3 micron, and that escapes the thermosphere, cooling it, and it's a loss then of kinetic energy from the atmosphere. Or the nitric oxide that's excited can undergo a collision, and that energy is returned back to the atmosphere. And so there's no loss of energy if that happens. And as I said earlier, the radiative cooling of nitric oxide is very dependent on temperature. It goes as e to the 2700 over T. And so it's very, very sensitive in terms of its being an indicator of the thermal state above 100 kilometers. And it's really, we've learned over time here, it's really a natural thermostat above 115 kilometers. As the thermosphere warms, let's say during a solar cycle, we see a large increase in nitric oxide emission, trying to shed that energy back out to space. And so it acts pretty much like your air conditioner does. When it warms up in the house, the air conditioning comes on. When it warms up in the thermosphere, the nitric oxide emission increases. And so we've been calling this a natural thermostat now for, again, about the past 15 or so years. And so how do we actually derive this information about the energy that's lost from nitric oxide? Well, SABRE is an instrument, as I said, on the NASA TIME satellite. We're almost 20 years on orbit. And if you follow this from the upper left-hand corner, you see there where it says radiance in watts per meter squared per steradian. This is what SABRE actually measures, the instrument actually measures. It's the limb radiance as a function of altitude from 100 to sometimes up to 300 kilometers in a very strong storm. We will see emission from nitric oxide. And the emission is optically thin. And so if you move over to the upper right, we can do an oval transform, mathematical transform on the measured radiance. And this is almost identically equal to the cooling rate, the amount of energy per unit time per unit volume leaving the atmosphere. And you see two curves here in the figure. One is during actually about 3 days before the Halloween storms in 2003. And the other solid curve is what we see during the Halloween storm. So it's quite variable. As you can see, a tremendous change due to the state of the upper atmosphere in just a couple days. So our next step is we take those cooling rates and then we vertically integrate them from units of watts per or nanowatts per meter cubed, and vertically integrate them. We get fluxes out of them, watts per meter squared, and that's over in the lower left-hand corner there. And that's a figure again from the over the duration of the Halloween storms. But then we area integrate that across the globe. So on a given day, we try to add up and estimate how much infrared energy in watts is emitted by the thermosphere on each day. And then we put together here in the lower right a time series of this, and this is just from 2002 to 2018, but it shows the great variability of the radiative cooling on a day-by-day basis that Sabre has observed from the thermosphere by nitric oxide. And you can see all the spikes there. Those aren't noise. That's real geomagnetic variability due to geomagnetic storms. And then you can see the solar cycle in there, the long-term solar cycle, as it decreases from 2002 to 2008, back up to 2014, 2015, and back down again. So it's this data product here, the daily global power, that we use to develop this thermosphere climate index. And so taking it a step further, we begin by looking at 60-day running means of this daily product. And you might ask, well, why do we do 60-day running means? And it's because the orbit that the time satellite is in samples all local times in 60 days. So in order to avoid diurnal or time-sensitive variations over the daily cycle of nitric oxide and temperature, we do a daily running mean, 60 days, step 1 day, the next 60-day average, step 1 day, and we continue to do that for the duration of the data set. And at the top frame here, this is what the nitric oxide 60-day running average looks like. We also do this for carbon dioxide, and we do that for CO2, and this is the power in watts, or 10 to the 11th watts, radiated by nitric oxide and carbon dioxide. Then we have the same average for AP, DST, and F10.7. And what we notice is looking at the nitric oxide power and AP, you see strong visual correlations between the two indexes, average here at 60 days. Some anti-correlations with DST, and also again, strong correlations with F10.7. And so we do a multiple linear regression between the 60-day nitric oxide power, AP, DST, and F10.7, and then we see how that linear regression looks and see if we can represent accurately the nitric oxide being radiated from the global thermosphere by this combination of indexes. And the answer is yes, we can. In the top frame here, you see in the green curve, it's the 60-day running average. This is the actual measured Sabre nitric oxide power, and the blue curve is the regression fit with AP, F10.7, and DST. And so we have a really excellent fit to develop a new index, which again we call the Thermosphere Climate Index, from existing solar and geomagnetic indexes. And the advantage with this new index is it tells us something about how the Earth is responding directly to solar and geomagnetic variability. And these indexes go back to 1947, so we can actually reconstruct what the entire thermosphere was radiating over that time from 1947 to today, almost 75 years. And that's what we have here shown here. This is the Thermosphere Climate Index going back from 1947 to about a week ago, where I have here solar cycle 25. You were here. This is as of maybe about 4, 5, 6 days ago. And you can see the progression from solar cycle 18 through solar cycle 24. You see the strong solar cycle 19 here at the dawn of the space age, a bit of a weaker cycle, stronger, and then the last 3 solar cycles seemingly getting progressively weaker. And we've divided these up into 5 different quintiles based on just frequency of occurrence of the various values to give them an adjectival description of cool, cold, neutral, warm, and hot. And we have been in the cold sector here for a while. Solar cycle 25 is starting up here, but it hasn't yet gotten out of the the cold region, even as of today. It's still, excuse me, it's still down here in the cold region. Now, one of the neat things you can look at is you can compare different solar cycles and different solar minima, and that's what we have here. So this is the TCI, the climate index from about 2005 until today. And if you look at the solar minimum in 2008, and you compare it here in 2019, 2020, you'll see that we did not get as low, if you will, in terms of the amount of energy radiated from the thermosphere. It didn't get as cold as it did in 2008. It got pretty close, but it didn't get all the way down to that level. So that's one difference that we see here. And someone mentioned earlier, F10.7 was a bit higher in 25 than in, I'm sorry, in 24 than in 23. And that's probably the reason we didn't get down as cold in 2019 and 2020, because of the extra energy from the sun that was coming in. Now, another interesting thing we see, you see these peaks here which show up, and I've put these lines here. Every 6 months at the equinoctial peak, we see a peak in the nitric oxide emission. And this is in the very single analyses we've done of the AP index. This is very clear. There's a very strong 6-month peak associated with the Russell-McLaren effect. And we see it very clearly here in the last solar minimum, primarily because there's not been as much other activity, as much, I think, as much geomagnetic storms as there was back in 2008, 2009, and 2010. So these 6-month peaks really stand out very nicely here. Again, they're present through the 20 years of SABRE data. They're present all the way going back in the TCI, but this is the most clear exposition of these peaks that you see. And I think this little bit that's coming up here, we're coming into the equinoctial time again. This is going to peak up here in the next 2 to 3 weeks and give us another peak that we'll clearly see here by the end of September. And then if we look here just though from what has it been in the last 4 or 5 months. So this is the TCI from May until yesterday. And basically what we've seen from May, we've seen a decrease. Even though we're in this onset of the next solar cycle 25, the thermosphere has been cooling down for the past 4 months. And you can see here the last few days, it's been going up. And again, I think this is associated with the equinoctial peak coming. I don't know that this is a indication of solar cycle strengthening. But as I say, since May at least, it has generally been going down. It's about 40%, 50% smaller back here in the beginning of September than it was in May. So I think solar cycle 25 is getting started, but from the thermosphere's perspective, it's taking a while. So in a summary, the TCI is a new solar terrestrial index combining solar and geomagnetic indexes. It does provide direct terrestrial context because the parameter that it is mimicking is the global power radiated by nitric oxide in the infrared from the thermosphere. It's a very sensitive indicator of global thermospheric temperature because of this nonlinear dependence on infrared emission and temperature. And it's been decreasing now for several months. It's a lot smaller than it was in May, but we do see this slight increase, this uptick. And there is a pronounced visual evidence for semi-annual variability in NO power, the Russell-McLaren effect at the equinoxes in solar cycles 24 and the beginning of 25 here. And so again, from the perspective of the thermosphere, solar cycles 25 has begun, but it hasn't really ramped up yet. And we can use this index into the future forever, as long as we have AP and F10.7 and DST. We can always have this pulse on the atmosphere due to the solar and geomagnetic effects. So with that, I'll step back and thank you for your attention, and look forward to questions.
Okay, thanks, Marty, for a very helpful introduction and the description of thermosphere climate index. And I'm sure people will find out how useful it is. So let's move on to the second presentation by Lan Jian from NASA Goddard Space Flight Center. Lan Jian, please take it away.
Let me see. Can you see my presentation now?
Yes.
Yes, you can just go full screen.
Okay.
We see it
How
now.
about now?
That's good.
Yeah, good.
Okay, great. Yeah, please let me know if it does not advance on your side. Okay, hello everyone. I'm Nan Jian from NASA Gauda, and I will talk about comparing the solar minimum between cycle 24 and 25 with historic solar wind records at 1U. Nat, Janet, Chris, and Tony are my co-authors. First, introduction, we all know the new cycle 25 started in December 2019. We extend our previous study about the minimum 23-24 to comparing this minimum with previous records, and also compare the large scale solar wind structures in the recent 2 solar cycles. Okay, here is a diagram showing the sunspot number in log scale for the last 5 solar minimum. This is 2 years around the minimum, and the magenta regions is for 1 year that will be used throughout the presentation for the statistical comparison. And we notice there are more spotless days for this minimum. And F10.7 and the polar magnetic field from Wilcox Solar Observatory, they are slightly higher in this minimum than the minimum 23-24, but they are weaker than the former ones. And this one is the maximum inclination of the heliosphere count sheet. It is flattest among the recent 5. Of course, I know this can vary depending on how you fit it and which magnetic field data you use. But it's a good reference, and it has a long-term record. Okay, the solar energetical protons and the cosmic ray intensity. Here shows the proton flux greater than 10 MeV, and you see the smaller for the solar cycle 24. However, there may be some effect due to the instruments and the emissions, and this one is the ground level enhancement events marked by the triangles, and there are few such events in cycle 24, and some of those are only stable GLEs marked by the light color. And the last one, the cosmic ray count, and it's actually higher whether using the mean or the median values in the minimum 24-25 than the previous ones. Of course, I mean, they are quite similar. Okay, so now I will talk about the solar wind parameters. Here shows the solar wind speed, proton number density, proton temperature, magnetic field, and their standard variation. This is from the Omni data. What I plotted here is 27 days, but for the statistics, I actually used the hourly data. So it's more meaningful, and in general, these parameters falling between the values of the first 3 and the last minimum 23-24. And you can also see interesting solar cycle dependence for most of these parameters. This one is the absolute radial magnetic field, and the southward magnetic field, BZ. They are not as weak as the minimum 23-24. The magnetosonic and Alpha speed, they are slowest among these 5, and the Mach number, they are similar to the minimum 23-24. This one is the solar wind impact on the geomagnetic activity. The 2 critical parameters are dynamic pressure and the east-westward electric field. And the black one is for the eastward and the blue one for westward. And they falling between, the levels of the foremost 3 and the minimum 23, 24 again. And using the early data, I checked the time fraction with strong geomagnetic activity. This is DST minus 50, and this is minus 100 nanoTesla. And if you plot it in log scale, you can see noticeably much weaker activity. In these two minimum, they are similar, and this is much less than the foremost 3. Okay, so that's the general solar wind and the geometric indices. Now about the large scale interactions in the solar wind. The first one is the stream interaction that's between the slow and fast wind, and they include the rotating interaction regions and the transient ones, which do not reoccur in one or more counter rotations. And when the compression is strong enough, they can form shocks about like a quarter of them are forming shocks at 1 AU, although it's more often at a greater distance. And we identified the stream interactions by virtual inspection using a series of criteria. And we identify the stream interface as a peak of the total pressure. And the key is the solar cycle variation of the SIR properties. And this is from 95 to 2016. I'm sorry, I haven't got time to update this to include up to 2019, but I have actually done that. So for the paper, I should be able to finish this. The blue ones are from Wind S survey. The red one is from stereo A and B. In later years, only in stereo A is available since 2015. And also I considered the available time. So the tallest bar is for the SIR count. The fader bars is for the rotating ones, which reoccur. And this is the SIR rate showing the reoccur more often in cycle 24. This just marks the corresponding phases for the 2 cycles. And also you see there are more stream interactions in cycle 24. And these are the numbers in the 2017, 2019. So it's really occurring more often. And this is heliosphere count sheet crossing counts, slightly fewer. And these are the association rate, noticeably lower, and possibly because of more pseudo streamers and also equatorial corona holes.
I'm sorry,
this is
half minutes left.
How many?
Half minutes.
Oh, okay, thank you. Minimum and maximum speed, and the speed increase are all slower, and the shock rate is higher, possibly due to the relative to the magnetosonic speed, and they last longer, wider, and the weaker in terms of the field and the pressure. This one is for the ISME, including the shock, sheath, and the magnetic obstacle. We identified them by virtual inspection and using a lot of criteria, and including the heavy ion charge states whenever they are available. And they are fewer events, and these are the numbers for the recent 3 years. And the shock rate is slightly lower, and they are slower and weaker, consistent with the weaker cycle 24. And here is a comparison of just focusing 1 year around the minimum. You see, although the minimum has fewer sunspot, but in fact, we still have seen many weaker ISMEs. And I checked in Richardson's ISME list as well. It's a consistent picture. So probably some of those are just like a blowout, and because of the quite a solar wind, we tend to observe them. This is the stream interaction regions more often, and associated with country sheet crossing less often. Here, just to show you the variation for the three minimum, the solar wind, the green, SME for red, and SIR blue. So you see the different variation trend, and also a deep minimum like 23, 24 does not imply necessarily implying fewer SMEs or weaker parameters. So this is a summary. We compared the solar wind and these SMEs, SIR's properties, focusing on 1 year around the minimum. And we would like to finish, the extend the solar cycle variation plot up to date. So that's all. Thank you for your attention.
Okay, thanks, Lanjian, for a very interesting presentation of solar winds at solar minima. So we will move on to the third presentation by Ana Elias from National Scientific and Technical Research Council of Argentina. Ana, please.
I will share my screen. And do you have the full screen there?
Yes, we do.
Yeah. Okay. Well, I will present a comparative analysis of UV solar radiation during minimum activity levels. And with this study, we mainly want to answer two questions: how different solar UV proxies behave around minima, and how well do they represent solar UV radiation during these periods. This is an outline of the presentation. We will see first a correlation analysis between solar UV proxies, followed by a comparison of some characteristics during the different minimum. And then as a way to detect the ability of each proxy in measuring solar UV during minima, we will analyze FOF2 long-term trends. And finally, a summary and discussion. Well, we begin with a correlation between solar UV proxies. We analyze 4 proxies: sunspot number, magnesium 2 core to wing ratio, Lyman alpha flux, and F10.7. We will consider monthly mean data. As an example here, I show sunspot number and magnesium 2. And also 12-month running mean, that is the low-pass filter version, where intra-annual variability is filtered out, shown as an example here for F10.7 and Lyman alpha. The analyzed period covers January 1979 to December 2020, so we have 4 minimum periods to compare. To begin, notice that each of the 4 indices we will compare is originating in a different region of the sun. Sunspots occur in the photosphere, magnesium 2 comes from the chromosphere, Lyman alpha in the transition region to the corona, and F10.7 to the corona. And here to the right, the variation along the quasi-decadal cycle in terms of percentage is shown and is estimated as the amplitude in a given cycle over the mean value in its cycle. With this, I want to show the sensitivity of each index to solar activity variation, and we have that sunspot number has the highest sensitivity, followed by F10.7, and the least sensitive to solar activity variation is magnesium 2. Going to the correlation analysis, we have as an example the dispersion diagram between the sunspot number and magnesium 2 considering 12-month running means to the left and monthly means to the right. In both cases, an almost ideal linear association is noticed with a correlation coefficient above 0.95, considering all the pairs between the indices I will analyze. So we could say, at least statistically, that they have a common forcing, which we also assume is the same as for the EUV radiation. Based on a work by Bruevich et al. 2014, we analyzed this correlation for subperiods in order to go through the different phases of the solar cycle and isolate minimum periods. In the figures, we can see the running correlation using a 3-year window for each of the 6 pairs of solar UV proxies. Here are the color code for each pair. And here is for the smooth series, and to the right we have the monthly mean series. The correlation clearly decreases for maximum and minimum periods, which are indicated in the figures by dashed vertical lines for minimum, which are also enclosed in these yellow boxes, and dotted during maximums. In general, solid lines, except the black and the dashed blue, present the greatest decrease during minima, that is all correlations with sunspot number, and that between F10.7 and Lyman alpha. So we could say that particularly Lyman alpha decreases its correlation with sunspot number and F10.7. In the discussion, I will give some more detailed analysis of what's happening here. Let's move now to some characteristic during minimum. We consider here each solar proxy separately in order to analyze some features of their behavior. We have here a superposition of the 4 minima, considering the 12-month running means: black for sunspot number, red for the magnesium 2, blue Lyman alpha, and green F10.7. 0 corresponds to the time at which each index reaches its minimum value at each minimum period. And solid line is for the first minimum. Here, solid. Here you have the code. Dashed for the second minimum, that is the one between cycles 22 and 23. Dotted, this one, is corresponds to the minimum between 23 and 24, which I will call the third minimum, and dot dashed, which is, this line, which ends here, the one that corresponds to the fourth minimum, that is between minimum 24 and 25. We cannot see here where the years, I didn't realize to put them here, but the minimum year for the different indices are almost coincident, especially for the third minimum, the one that occurred in 2008. It's almost the same date for every index. The order of the minimum values is first and second, these two, the highest minimum, followed by the fourth minimum, that is the one that of 2019, and the lowest minimum is that for 2008, except for the sunspot number. This is the only exception, but F10.7, Lyman alpha, and magnesium 2 presents a little bit, a slightly higher minimum than the previous one in 2008. Another thing we can mention is that lowest minima corresponds to longer duration, similar to the inverse relationship between solar maximum level and solar cycle duration. And well, that also something very common, and we all know, is that the descending branch takes longer than the ascending branch here in these curves. Let's analyze now FO-F2 behavior during minimum as a kind of witness of the solar UV variation. FO-F2 is the critical frequency of the F2 region in the ionosphere. It is a measure of the maximum in ionospheric electron density, which occurs around 300 kilometers height and depends directly on solar UV radiation, which is the main ionization source, at least at mid and low latitudes. We will consider FOF2 from two Japanese stations, Kokubuki and Wakanai. Sorry for this, I did not analyze this one. I forgot to delete it. And FOF2 long-term trend values behavior will be as a thermometer for the four solar indices efficiency as EUV proxies. Here is a very brief description on long-term trend estimation in FOF2, where the first step, which is here, is the filtering of solar activity effect, which is a key step in trend estimation. And then the trend is estimated from the filtered FOF2 series. Long-term trends in FOF2, especially decreasing trends, are expected due to increasing greenhouse gases concentrations, such as carbon dioxide. This expected effect, however, is very small, not more than 4% or less of FOF2 variability. Suspecting that during the last two minima, EUV solar proxies may not reproduce adequately the EUV level, here is what to expect if this is really happening. Here, if EUV is higher than the level indicated by solar proxies during the last two minimum, then trends estimating, including these periods, should be more positive than without the two periods. Here is the opposite behavior in the opposite case. And if EUV behaves perfectly like solar proxies shown, then trends should not change. Then here we have the trend values considering the whole period of the data, all the periods without the four minimums, and the complete period without the last two minimum. In generally, it can be observed that the more stable trend values are obtained with magnitude 2 in the first place, followed by Lyme and alpha and F10.7. What does this mean about the EUV proxy wall? At first sight, we could say that these are best proxies for solar EUV than the sunspot number is, and particularly for the sunspot number. If we check the trend values with and without the last two minimums, that is this value and this value and this one, we see that trends are more negative when the last two minima are included. According to what I have just said, this would mean that it overestimates EUV levels during the last minima. But here we have a problem because the sunspot number cannot go lower than 0. So it's like, even if the sunspot number would have to go lower, it can't. In fact, if FOF2 values close to 0, assuming that can happen, that would mean negative sunspot number and F10.7. But in the case of magnitude 2 on Lyman alpha, no, that would be good indices to do this. And now let's move to the discussion and conclusions. About the correlation coefficients between any pair of solar EUV proxy, it is very great and greater than 0.96. And when we focus in shorter periods, it decreases specifically during maximum and minimum periods. A possible reason for this is purely statistical. Here is a little statistical play that I have made. Here we have, for example, an 11-year cycle. For example, the EUV. I add a random noise of much smaller amplitude. Here is the resulting series. And if I make two series like this and I make a running correlation between them, I obtain exactly what I have just shown you with the solar EUV proxies. And well, the problems here is that the decrease during the minima and maximum periods is due to the EUV varies very little. So the only thing that varies there is the random noise. And since random noise are not correlated, that is why the correlation goes down. So there will be no physical reason for that, just a statistical reason. And going now to the trend results, magnitude 2, which is the least sensitive to solar activity, would produce the most stable FOF2 trends. trends obtained with sunspot number are the most unstable. So the answer to this question, if this indicates that magnitude 2 plays the best role as the UV proxy, looks like yes. We have some other analysis that I am not showing here due to a lack of time. Another possibility.
Anna, 1 minute.
One minute, yes, yeah. I'm just finishing. Another possibility is that the association between FOF2 and solar UV through its dependence with proxies should be revised during minima. I have just seen a paper which says exactly that the same linear relationship along most of the cycle does not hold during solar minimum. And going to the superposed epoch analysis, we deduced that the first two minima are clearly higher than the last two, with the one in 2008 being the lowest. And in terms of percentage relative to the solar cycle amplitude, even though the differences between minima are all similar, it is greater for sunspot number. And this is kind of in contradiction to what we just deduced from a FOF2 trend analysis. In conclusion, we have yet partial answer and still our two questions about the role of each index and their adequacy to measuring EUV are still open. Okay, thank you.
Okay, thank you, Anna. So this is a very interesting analysis. All these four indices are very important to look at the geospace response to solar activity. So with that, we will move on to the Q&A and discussion portion of this session. So Juliana.
Yes, I think we can start with Pete Riley. Had a question for Len. Pete, if you want to unmute yourself and ask your question.
Yeah, thanks. So Len, that was a very nice presentation on the statistics of the CIRs and CMEs. One of the slides, I don't know whether you can bring that up again, showed the number of CIRs and SIRs as a function of time. And there was the overlap between wind and ACE and stereo during 2007 to 2009. During that time period, it looks like the stereo numbers were systematically underestimating the values that wind ACE. Yeah, exactly this one.
This one, right? Mm-hmm.
Yeah. So in that in the second panel, event count 2007 to 2009, where they overlap, you're getting consistently higher counts from wind and ACE. Do you know why that is?
I don't exactly know, but I can check. And I mean, the difference is not. I think it's less than 5 in some of the years, right? Like here.
But that might be, let's say, a 25% difference. And if it turns out that stereo is incorrect, then that means that you're probably underestimating them for the rest of the time period. So like in terms of, if we're trying to see variations from 1995 to 2015, do we need to correct one data set with respect to the other? And I guess if you said it was because stereo's instrumentation was not as good and couldn't detect them as well, and so your algorithm didn't pick them out.
Yeah, I don't think the stereo because it's a basic solar wind observation. I mean, it's a plasma and mag data, and that quality is sufficient for the SIR identification, so that shouldn't be much a problem. But of course, I think I showed in my in one of my paper too. Sorry, I mean, if I take too much time, let me know. But maybe this one. So you can see like from because I'm trying to move from here. Maybe I compare like a stereo A and a stereo B.
Okay.
That the event count. Sorry. Did I compare? Oh, not here. So maybe the ice. Not this one. This, however, this is ISME. But the event count can differ much. I mean, noticeably between A and B as well. It's you know, it depends on the relative location of the spacecraft to the the heliosphere count sheet. In this case, for SIR. So if one spacecraft, because also such structure is co-rotating, I mean, it's recurring, right? So if you miss one, it's likely you will miss the following few of those. Yeah.
Okay. All right. So maybe it's not a systematic. Maybe it was just an unfortunate coincidence that makes it looks like it's an offset.
Yeah. So in general, I think you know, within more points, the statistics should be more sound, including the properties. Yeah.
Okay. Okay.
But I can check. But I will check. Yeah. To see
also,
this. Yeah.
Also, as a quick follow-on, why did you stop the wind ACE analysis in 2010, 2011?
Because I haven't got time to do that.
Okay.
Yeah. Yeah. Because I graduated. Okay. The dissertation is done.
Right.
But yeah, I have developed a way to auto-identify them. I can use them again throughout the data, so that will remove some of the bias from the virtual inspection. So yeah, that's something doable. Yeah.
Yeah.
Thank you.
I agree. It would be interesting to see. So now we can go to another question. Ying, and a question for Marty about the TCI index.
Okay. So Marty, I'm thinking about this. Can TCI be used to detect the climate change in the upper atmosphere and also to understand the climate change? And if yes, how to do that?
Okay, thanks. And I'm sorry, my connection timed out and I came back in just now, so I may have missed something. But the question about using the TCI for understanding climate change, the short answer is no. It can't be, because the TCI is the energy output from the system. And the energy output is can only be what the energy input is to the system. And so as the thermosphere changes, the composition changes due to climate change, the thermal structure changes, it still has to emit the same amount of energy that comes in on climate timescales. And so once you evolve or account for natural variability like the solar cycle and remove that, there really ought to be no change in the long run of the energy coming out unless the energy going in is changing somehow. So it would not really be a good indicator. We have to really look at the physical parameters within the thermosphere, the composition, like the CO2 increase, the temperature, the the temperature decreasing. But basically, in that case with the CO2, what happens is you increase CO2, the temperature decreases, but it decreases in such a way that it still emits the same amount of energy, but at a lower temperature because you have more CO2 in the atmosphere. So energy like this is not a parameter that you can use to diagnose climate change. It's because the infrared energy is the response to the exhaust of the climate system, basically. It has to just always be whatever is coming into it on the climate time scale. It's not actually a parameter that adjusts to climate change. And one other way to think of it is that when CO2 increases, and since CO2 is one of the cooling mechanisms, one might think that, oh, well, more CO2 means more cooling, but more cooling means a warmer atmosphere. But the effect of CO2 is to actually result in a cooler atmosphere. And so that, when you think through it, you just come to the conclusion that in the thermosphere and in this mesosphere and stratosphere, CO2 behaves differently than it does in the troposphere. These explanations I'm giving right now are not relevant to the troposphere because of the timescales of radiation, the timescales of energy storage and so forth, and various feedbacks. But it's much simpler up in the upper atmosphere. And it's really, again, it's an energy parameter, and it does not tell us directly about climate change. And so I hope that quick answer was clear. And if not, please, please ask. I'll be happy to follow up.
Okay. So if you, so you said that's a quick answer, but if you dig deeper, if you say there's more CO2, there's more CO2 cooling, and it sounds like the total cooling is dictated by the energy coming in. So maybe you can, through looking at the ratio of like NO cooling and the CO2 cooling, and maybe there will be something, because now you have more CO2 cooling, and wouldn't you have less NO cooling?
You don't have more CO2 cooling. When you put the CO2 in, the temperature decreases. It's the product of the what we call the emissivity, which is in radiative transfer. It's a product of the emissivity and the source function. The emissivity depends on the amount of CO2. It's the amount of CO2 and the spectroscopic properties. The source function, think of it as the Planck function. It's proportional to that effectively. We won't get into the non-LTE aspects, but the Planck function depends on temperature. But because over the long haul, the amount of energy that comes out has to be the amount of energy coming in. If you put more CO2 in, you increase the emissivity. But for the energy to remain constant coming out, the temperature has to decrease. And so you do not get more CO2 cooling. If you got more cooling, that would mean more infrared energy coming out. And the only way you get more infrared energy coming out is for the atmosphere to increase its temperature. That's fundamental radiation physics. Warmer objects emit more energy, cooler objects emit less energy. So as the thermosphere cools, it has to, it's still, regardless of the CO2 amount, it can only emit the amount of energy coming into it. It cannot, all of a sudden, you cannot change the structure of the atmosphere by putting more CO2 into it and make it emit more energy. It will cool down to, with more CO2 going up, the temperature comes down so that over the long haul, the amount of energy stays the same that the atmosphere emits. So it's not correct to think of the atmosphere of increasing CO2 that you get more cooling, meaning more infrared radiation from the atmosphere.
Okay, I guess it's a lower equilibrium temperature of the system.
Right, the temperature goes down, that's correct. But the product effectively of the temperature and the CO2 amount remains constant. In a very coarse way of saying it, it's more complex than that because it's not linear dependent on the temperature depends, again, it's like the Planck black body function, not linear on temperature, but it is effectively dependent on temperature. So you increase CO2, the temperature has to come down to keep the amount of energy going out. And so you don't get more infrared energy coming out. You have more CO2, you have lower temperature, but their combined effect is still to emit the same amount of, or whatever energy is coming in.
Okay, thanks.
Yeah.
So I have a question from a non-expert. I remember during the past minimum, there was a question about the change in the thermosphere, how much was driven by the low activity during the minimum and how much was simply anthropogenic change and cooling due to that. So do we have a better understanding now how much is the forcing? And now that we have two low minima, can this give us some insight of what's going on?
We have an excellent understanding of that, and I'm about to submit that to JGR. Let me, well, I don't know if I should show a result or not because it's not been submitted yet. I can just tell you that at 10 to the minus 4 hectopascals, about 105 kilometers, the changes that we see over the last 20 years in temperature at that pressure level, we see about a 22 Kelvin change in temperature in the global annual mean temperature at 105 kilometers. About 6 to 8 K of that is due to CO2 increase, apparently, and the rest is due to solar, the weakening solar cycle. So it's about 1/4 of the change is CO2 increase, and the other is due to, the other 75% is due to the solar cycle over the last 25 years at 105 kilometers. That's one of the results of our paper that we see. And as I say, I'm about to submit that to JGR. It is a new result that we've got from looking at SABRE data.
Okay, looking forward for that. So the next question is from Sarah to Jan.
Yeah, and it's just something I've wondered about before. You showed that figure showing 4 solar cycles and solar wind parameters, and I've always noticed that the solar wind is very flat in cycle 20. Do you have any thoughts about why in terms of the IMF? I mean, the other ones you can see the solar cycle in the variation. you have any thoughts about that?
You mean the initiation inclination angle, right? Of the
No, actually, I mean, you might want to just show your figure. It's the one where you showed solar wind you showed the BR, you showed like several magnetic variables, and I was just curious, maybe it's something obvious that I'm missing. Do you know the one I mean?
I would like to show this. Is it okay? Because I need to stop other screen sharing. Okay, all right.
Should be.
So it's okay. Share.
It'll be much easier.
All right.
It's about 5 slides back. 5 slides. Or yeah, it was a ways. It was like there.
This one, right? BX.
You see how you can see the solar cycle in most of the other ones. You know, you can see a correlation or something with sunspot number, and I don't. It just looks super flat. Do you have any thoughts about why that is? It's the same spacecraft that's measured?
You mean this is super flat?
Cycle 20.
Oh.
Yeah.
Good. Yeah, good question. Because you know, earlier the time we don't have as many solar observations, so it could be because of the the gappy data, and this is 27-day 27-day data, so that may affect this somewhat, but it's a very good question. Yes.
I don't know if anybody else. Oh, Ian has his hand up.
Yeah.
Go ahead, Ian.
Yeah, I mean, this is well known that the IMF increase for 20 was very small compared to the others. It's always been a bit of a puzzle. But I find the paper I looked into this a bit more, and it turns out the Omni data course is made from a whole lot of spacecraft to knit it together and normalize and so on. So if I remember rightly, the IMF data is actually continuous through this period, but the plasma data has a gap. But anyway, it's not the question of the calibration seems to be fine. It's really low in that period. So, and in fact, you can look at the GMT activity. I think Don Fairfield did a paper, this is going back decades, but just comparing the GMT activity in the different cycles, and you can very clearly see that the IMF and so on was very weak in that cycle. And so it is actually a real effect that the IMF is low in cycle 20 for some reason.
It's low, but also the variation between minimum and maximum doesn't seem to be noticeable.
Yeah, I think the intensity is a bit more noticeable. It seems to be, if you look at the intensity, it's a bit more known. There is an increase there, but it's far more weaker than the other cycles. Yeah, it's been a puzzle, particularly in cosmic ray modulation. The cosmic ray intensity tends to be inversely proportional to the magnetic field intensity, but the field there increases very weak in cycle 20. You can see a modulation of cosmic rays, and we did do a modeling that can explain that, but it's been a puzzle why 20 is different. Yeah.
Okay, and did they actually have like a continuous 1 AU observation, or is from other region and normalized to 1 AU?
It's sort of one near a spacecraft, yeah, because the coverage isn't quite so good in that cycle as cycles, but not too bad. I mean, there are some gaps there, but you can very clearly see, I say, particularly using proxies for the IMFs and GMT activity and so on, you can see that this cycle was actually, that the IMF was actually weak. It's not just an observational effect.
Okay, sorry for the interruption, but we have 1 minute.
Oh, sorry.
Yeah.
Yes, Janet has her hands on. Maybe she can make the final comment.
Yeah, can you hear me?
Yeah.
I just wondered, there was a period when all we had was IMP8, an Earth orbiter. And so we didn't really have very continuous data for solar wind. Is this a period where IMP8 was the main source?
IMP8 should be later, right? I mean, because it's like cycle 22 before the launch of wind, right?
Yeah.
We depend heavily on IMP8. Yeah.
Right. So if we were relying on IMP8, not only do we have the gappy data, but we have the Earth's foreshock in there. So it's
not the best data for this interplanetary evaluation.
Okay, so
Okay, thank you.
Yeah, so because our session, the time is we actually passed 1 hour. So would you please? I will ask the speakers to go to the Slido to answer question and also keep a discussion going on, you know, through email or yeah, and or later at other discussion session. And Juliana, so do we? So I think we will keep the question in the slide will be people can see those questions, right, Juliana?
Yeah, people can see the question and they can, the chat can still go on in Slido.
Okay.
And we will have time to ask questions in the following open discussion.
Okay. Yes, yes, so we need to wrap up this session.
So we need to wrap up, but thank you to all the speakers.
Yeah.
And the question and from the audience.
Yeah, thanks for the speaker, yeah, and everyone for your contribution. And we conclude session 7, and we will go on a break, 10 minutes break, and reconvene at 11:55 for session 8. Yeah, thank you.